Yeah. Okay. Yeah. Wow.
I'll let them know.
Okay.
Puts you all in touch. But right. That's fine. Yeah.
I don't know, like, about the continue. No. Let's see.
Throw some in.
Yeah.
Essentially, I think again, things that are being done.
Oh, is that what you were Yeah.
So whenever it's ready. Very nice. I don't see a broken hand. Never cycle with this guy. Half of the people cycle are in bandage in hospital. You're lucky.
One of our other colleagues, he broke his cheek with the cycling. Landed on his head. So experienced.
You're insisting every day. Can I pick you up cycle?
That was not nice, Ken.
Yeah. Yeah.
Get your stable and zone something.
So if anybody needs alcohol,
I don't think you have any discount share between people outside. No.
but still you can keep the levels there.
I guess it is still not like the microphone.
Right.
No.
Here, in this laptop,
Generally, the YouTube video sound was.
I think this YouTube is going to be more.
Share.
Oh, it is shared.
YouTube is public.
Oh, yeah. We are not trending across the world. That's probably. Yeah, this is a reading and bad related. I just put my book down. I just touched the corner of the bedside. It wasn't even hard. That was so just like, just like a sharp corner. I can touch it. It's like hard.
The rate's money.
We are.
yes.
Right, that's you.
Nature work.
I'm getting an unfairly bad reputation now. This one very hard for us. I saw the spam the other day, yeah?
No.
Yeah. It's obviously comprehensive. Yeah, how many lunches? We can just use
It has its submission to which I said, thank you, but I don't think he accepted.
Really? I'm good.
Yeah, fine, thank you. Is that?
center system. CC.
Bring this over.
Well, yeah, you're gonna put this so everyone can see.
Can you stop the screen sharing, please?
On the other one.
Very good point to that. Like that.
It's in the top.
Not sharing screen. Okay. So yes, we're gonna try some demo hands up today to see some of the tools we talked about yesterday. So here are Jake's data set. So we'll talk about it, and then Andy will show us tool set. But a lot of the talk will be in the afternoon, so I guess the theoretical part is in the evening or afternoon, and the demo one.
Yeah.
Okay.
All right. So, Jake, I don't know if you want to give some background into the data.
Sure. This is, this is just a gold standard reference file. It's from one of the validation experiments we ran. First setting up the center in the nice. We run about 10 planes worth of experiments, and this is exactly halfway through that. It's exactly halfway through the fifth plane, so it's just what we consider an average sample. And we use it for a lot of our testing of these kinds of operations. Yes, it's zero. Shoot, I mean, what it is.
All right. So, this is the tool that Richard described yesterday. Got the two areas really, so the noise reduction side and the compression side, which you can also expand as well. Simultaneous, two-way operation. Parameters are set. Dialogue. As Richard suggested, there are three default settings: low, medium, high. So go for the low option, I guess.
So that's the question of that. So we go 5 retainers, or 6, or rather reject.
Will reject more.
Higher threshold will grow out and stuff.
Higher threshold will let more, keep more, retain more.
It's like breathing.
Yeah. Lower
So
threshold.
it's not the baseline setting. So 5 would be the sort of threshold lower,
Yeah.
and would be higher.
Technically higher. Takes higher again. So if you remember Richard's slide at the end, the histogram.
Medium, low,
Yeah.
high.
Yes. It's effectively being harsher if you throw more away.
So the higher number there gives more compression, less compression.
Reduction, it gives less, I believe.
Less reduction.
Yeah.
Obviously, you've done
Because you're allowing more in, I believe. I believe that's the way that it is.
We'll try.
We'll find out. Yeah. So we'll go with the So I'm just going to put the noise reduced data in the same location. So it's 70%. So set. The suffix is, it won't overwrite the original raw file. So it's going to create a new raw file with that suffix at the end. Underscore n or dot raw. I think if you remove the suffix, you may actually overwrite. So, do that until you're comfortable with doing. Start the question. There'll be some process information here as it turns through. Data file, previous data files we had for you to sort of look around the 5-minute mark. This one.
I expect that to be about the same. Once you count down, I've got I've already done the piece. So
So you can see there's already a new folder in that location. It has some spurious numbers on it, which the algorithm comes out of the data somewhere. I'm not sure what they correlate to. That's just to give that temporary output folder a bit of an identifier while it's working on it. You rename it to the convention specified one.
Which one do you usually choose as the first one? Or try it?
I do this for signals. That's basically trying everything much as I can. Never see reason to regret it. But you should make every reason to testing.
I guess that we can test case if you try one and see how much they can probably use.
Yeah.
So,
Well, like I was saying yesterday, I think at least a great majority, 85% of the data we use is things that have been studied through a sort of data production stage anyway. Some of it's taking I don't see us leaving any significant information. And by its nature, what we do is these small weeks that are so close to the detection. I'm genuinely worried about the appropriateness of asking those sorts of analysis.
Reducing it in this way that will affect on the data processes everything wrong.
Yes, so
Using
if you
somehow to
yes, if
process
you find less peaks because there's less in the data set. I think that's to be expected because pretty much you find enough noise.
What about the estimation of noise, for example? So, you remove the noise, you do believe the estimation of the noise is different.
Yeah, I can actually investigate that. Yeah, but so it's always a matter of things that we can standardize.
So, there's a ballpark figure of 85%. Imagine talking to collaborators and saying, we've got the fire alarm, I'm feeling
Yes.
well, obviously, that's
Yeah.
but I mean, that is a consideration. It's 85%.
Yeah, well, as I say, I'd rather work my personal on the 85%. You know you can do something useful in the future. It's just so close to pointless.
But I guess if the 85 is strongest 85%, then 15% it's not actually quite that far away.
Yeah.
If it's 15%, send it back to the select.
What cross study the values that you're going to choose if you choose sort of this reduction over your NAs and missing values? Would it be now everything to be set to 0 because for some of the arbitrary numbers because you don't have any baseline?
Trying to match this back to
Cross many samples. So you have a peak in one of them, which is let's say review, but it's missing the other one in other samples.
So one of the, because we use a sort of dilution series based on our Stoney reference for one of our primary filtering, so for both filtering on CVs and correlation to dilution. Essentially, if the sort of feature doesn't exist in the Stoney reference, we don't retain any, sort of get excluded at that point. So we're only picking up features that we're only least existing Stoney reference. So we should have thought of for example, the entire study. And you know that has the limitation of potentially diluting out very small contributions from individuals. If there's only a handful of samples in the study that have very low levels of by its nature, we'll use that would be different. You see, but I don't see any good way to estimate the reliability of something given with a line. You only see it 1 or 2 spectra across the entire study. You can't safely use that information anyway.
If you have a study of 10,000 people, and it's a feature which is better than 200 people, this could still be very relevant profile.
Yeah, I mean that's the.
But you will lose that. We have exactly the same problem. How to deal with those things. But I got asked by an epidemiologist how about vegetarians, markers of vegetarians. In this study, it will be about 5% vegetarians. This approach will be used as well. We will lose those markers. So they get presented out so much.
Essentially we've been lucky in that the studies we've done so far tend towards either quite well designed populations where they design the cohorts such that you have fairly representative members of each of the subclasses they're interested in, but reasonable proportions of the entire data set, or stratified medicine kind of studies where again it's much more case control or a few clear groups. So we haven't quite had the problem of where we're expecting to look for only a handful of few percentages of the entire data set. So we've felt it's safe to implement so far.
Okay, so on that original data file was a 2.5 gig, around 200 gig. So that's with the rest.
What I was trying to do here is actually, because I've got the spectra loaded up like 4 long spectra loaded up from messages. Unfortunately, I don't really know how to use messages.
Don't look at me.
I was just thinking if anyone wants to actually see.
Yeah, that's one of the uses.
So,
If you convert one of these data reviews to sort of ML, would you easily convertible? Nothing.
yeah, actually, so when I was pointing out that you see this sort of strong size inflation converting to NZML with the raw data, actually after the noise reduction, we see a slight size reduction to, well, not to NZML, but to NZ5. So it's actually more compressible in those formats than the original data. And the other thing, should I just unplug you?
Oh, I've got it from here.
Oh, you've got it open. Fantastic.
It's the same data.
Yeah, no, you go ahead. I can just dig out the outside.
I can relate it. Someone else can relate to what
If you just point down to say around 300, that's see something like this here, I think it's very unlikely there's anything real in there.
Depends what you mean by real.
Yeah, sorry.
Real metabolite in the sample.
Real information.
Real iron.
Yeah. Something is being detected.
So if you would look at this 325.8 and then look at the chromatic value, get a real peak for that.
So the noise reduction here is being done in 2 dimensions with the chromatographic dimension. Is that correct?
I believe this has one degree this with the adaptive factors.
Okay, so it's just done in the mass dimension. So that it's not close and that it's not deciding whether there's a proper chromatographic.
It's not a, yeah, as far as where it's purely found, this is more I can see signal in it. It just sits over the threshold that we picked.
So maybe it's 325.8, it's probably not the real metabolite.
Yeah, exactly. So as you scan back up and down the spectrum, you will see bits of noise that are retained.
Better that way around.
Exactly.
So that's
This is one of the reasons I've been fairly happy with the quite aggressive sort of setting on the filter because you're still retaining some of it.
So the noise removal is, I'm just trying to think, if you were to do this across lots of sample studies and that kind of thing, does it maintain comparability of 2 different samples as much as you can do that in some things that we learn?
Yeah, I know.
So it's kind of a local noise reduction. So, I mean, imagine you have a bit of a spectrum where the local noise level is much higher than elsewhere. You'll have a different kind of overall level of signal retention than you would somewhere where the noise is very low. Or in a spectrum where the noise is higher, the spectrum is low.
We've got a couple of sources of noise in this data set, and I think what this is particularly good at is this just consistent low level background fuzz, which it's not like say the undifferentiated peaks you see that can't wash and stuff going on. It's just kind of the general. I mean, you could zoom into almost anywhere in the spectrum and see something like the noise that you see. And so yeah, there are other sources of noise which this is less.
What's the actual number of count? I can't remember that number 58 in green, that number wasn't right now. So is that the maximum number of counts in that particular view? I think it is. The high speed has 58 counts.
Speaker.
So I mean, yeah, I don't know. I mean, my impression is that even down at that level, there's still real mass gap peaks.
Yes.
But maybe it's
Yeah. It's, from my perspective, their real peak source is less interesting than the report.
yeah. But I think that's something that has to be clarified very carefully. What was the real peak? Analytical people, and they say, it's not a real peak. Probably quite a big number of counts, but they're discounting it or something. Peak shape or something. Data analysis.
There's different tools.
graphs.
And if it's present in one scan but not all others, are you removing it if it's present in?
God, your maybe just
mean, to me, it's no, it looks like it's doing a relatively good job. And no, from my point of view, if you've got something in that glass, you're not going to use that. You're not going to be able to because it's just going to be the same. So it's like how I do it. Yeah, just really good to get processor. So,
For me, just most critical is zoom in on the actual real sequence, the actual. We're not doing the actual deep shape, and it's something that where you have expected small isotopic peaks down the spectrum, they're typically still there in some of the smaller signals. So that gives me confidence in seeing something reasonable, shall we say.
We can try some of the high threshold.
Try another one.
Yeah.
We haven't discussed the sort of general viewpoint of lossy versus lossless compression. This is a particularly lossy compression. Whether perhaps by default you will say, oh, let's go for lossless compression first.
Well, this bit isn't doing any compressing, this is actually.
Yes, but stage. If you think of it as a compression approach, then it's a lossy version.
Right.
Yeah. But
So I'm going to show a little bit later what we've done in the Proteomics Standards Initiative for lossless compression. It's slightly, because I guess there's a medium as well. This is definitely lossy, but you can go for what is technically termed statistically lossless, which is where you keep the bounds of each data point within a certain, say, percent or 0.1% of the original value. So the problem with fully lossless compression is that noise in itself, the entropy means that it's impossible to compress. So you can easily compress all the signal, but you can't compress the noise. So with lossless compression, you don't get that great compression rate. But if you just like go statistically lossless within a count, you can attain much higher compression rates. And I guess nobody's going to be too worried about a count here and there, because you're talking here about
something
many.
interesting to compare the compression ratios to something like that versus something like this, which is a bit way of doing compression.
But the big question is you think about the long term. So a data set that you want to last for many years or maybe, and considering that some people go and de-analyze the data, the volume, traffic of the data, or storage and all that criteria, as a user, and you already reuse some of the data, which format do you prefer? The lossless or loss?
Well, I suppose one thing to say is 10 years' time, is somebody going to want to download and analyze the noise structure?
Always somebody.
You know, I can imagine that actually being something quite nice to do, but then that doesn't necessarily mean that every single data set has that way.
A system that caters for 90% of the people.
Yeah. Certainly, analysis of noise structure is actually a valid Yes.
One thing it would be useful to get an indication would be from the vendors of exactly how accurate their detection capability or the baseline of the detector noise or whatever in their system. Because, for instance, in a flight, a lot of vendors are storing integer ion counts. And that's all right. But then you have Thermo that stores the intensity, but it's stored as float, so it's stored to 30 decimal places. And what's acceptable for truncating that? Because if you're storing 30 decimal places, you're never going
in the afternoon, you have, I don't know if anyone's online, I don't think anyone's online, but maybe I'm wrong. But in the afternoon, there will be people from Perm or group here, and so anytime. So you can ask the same question, maybe get some sort of their feedback. Yeah. I don't think anyone's online. I don't think this is really needed. They show you down these things to the website. Yeah. So it's just only via web.
So that was 15. That's actually reduced as much as this. 15 is more.
I did.
Where was it? Sorry?
So it's 302.
Yeah, the ISO 3.1.
So one question is, how do you gauge what the sweat of cheese to go? Yeah. Yeah. So it's a signal to noise issue with the isotope peak, so signal to noise of 5 or something.
I guess for our lab, you could say that we're obliged to keep the raw data to explain how we got the results for our customer. You can use the rawest version or the less clean version to do distance and your result of production, and then try to reduce the data as much as possible to still reproduce that result. So you use the rawest version, and then after you come to your conclusion, you can clean it up and see what version of the compressed or the clean version still comes to the same.
So that would end up having different compression and noise removal parameters for different
I
sizes. So.
You have an API of some sort. You can use it from any language, command line or whatever.
We've written an automation tool that would allow you to run this via the command line. So immediately post acquisition, you can
Automate the
Yeah.
process.
Yes. It's a separate product, but yeah. May not be mass linked, it might be unified first, but it'll be for a particular instrument and the acquisition system for that.
So I think you could make it up that it is all data.
Yes, yeah. So a plan moving forward will be to start with a particular instrument and integrate this into the acquisition software. But then through the other, going to become really that automation piece. Legacy systems can still use the same noise reduction tools, but post acquisition.
Is there any other, there's quite a few operations that go on inside the instrument to either in the electronics or in the software before we can get raw data. Wondering if there are other operations, not essentially, but other things which effectively do some compression or noise reduction. We don't know.
But certainly it's great.
That's the obvious one.
One of the things I think is kind of clear to us is just how different synchrotic parameters are between different instruments. I'd say that different massive SCNs have different synchrotic parameters which are easily not documented.
And does the user have much
control or any control.
That's completely honest. It's one of the most efficiency. So
These continue.
these will continue.
These are
I mean, is it applicable to central data?
no, not right now. Continuum on.
Yeah.
What's the reason they have a little medium line?
I think it's sort of just ease of use, really.
Yeah, I must have misremembered, you know, people looking at the ultimate pressure ratio rather than the top ends, because typically you see that most of the things like that make it. I expect to see like a couple of bits of sitting around, but still great.
So the top end is the one
More aggressive.
of these granted. So the
Seems the higher value was more aggressive.
Yeah. So that's
High value is its on.
That's the last one we gave.
quite low.
That's 15 laps.
Yeah. I think session is
5 is the granted towards the end, right?
For this data seems to be.
maybe gentle weights represented on the software instead of a little bit higher parameter that makes the sort
Yeah.
Yeah, I mean, unless that number has a direct interpretation into counts, say,
Yes.
you know, if it's 15 counts as the threshold, you know, that makes some sense to use it, but otherwise, it's
Not clear.
clearly. um, yeah, it's just thinking it'd be interesting to see a kind of analysis of, you know, the different values of the parameter or pressure ratios you have. I mean, presumably it's not linear, right? So,
Right.
you know, if somebody lowers that down to parameter value 1.
Yeah.
So that has to be doing one again. You know, if it goes above 15, is it not doing much?
So wipe everything out.
Right. And the amount of compression is what they said.
It is. So let's see into it on proteomics data, you don't get the same amount
Less reduction.
of less reduction.
So this will also incorporate plus compression. So that's also
The archival,
yeah.
yeah.
So it might be
Maybe we should try that.
You can, right, when I run that, so you notice that we've got these suffix raw effects, you know, output. When you activate the archival bit, it actually takes that nitrous use bit and then zips it up and replaces it with this version. So
Or is it just a standard zip?
it's not. It's special. It's based on the standard zip, but they do something custom to it as well. I'm not sure what it is. But you can, they call it WCT, which just is an acronym for the tools that works compression. You can effectively reinflate that back to
Yeah.
that's
That's
almost.
lost.
We can run that. Just do it on the 15.
So that's it, going to do noise reduction again.
It is, but with the same parameters that we had. I've just added the 3 just so that I don't overwrite anything. And then if I play in the archival piece, that means it's going to do the any standard zip compressor.
Can you just take the one that's already been produced and just do the
I'm not sure. Doesn't seem to give me that option.
But there are some times that both can work. If you using it and taking away and then still is
Does.
less compression.
Yeah.
So that means I can go back into the full row from somehow.
No idea.
Jeff, have you tried any data set that is very some sort of EQ data, for example, that's the quality data.
Yeah, exactly.
It's just based on some sort of, because I remember from the talk, Richard said this is sort of a signature from a chemical matrix.
Yeah.
So it can detect a sort of kind of signature pattern rather than a noise. Because again, sometimes it's really interesting to see whether those are still there or not.
Yeah.
So with the additional architecture, so that compression, you get down to 29.
And that's probably one that was 93.
Yes, so that's got that level of noise reduction.
So from the 94 down to 20 meg is lossless.
That's the lossless compression. Yeah. And the original demo is 2.5. Yeah. And then you can get back to, from 29.5, you can get back to the 94 in this. Yeah.
You can essentially compress that.
Yeah. But you could just compress the original with the noise and get back to that. You just don't run the noise reduction step.
But you don't know compression routine or
Sorry?
what compression routine.
I don't know the details. There are white papers, so Richard said he was going to try
Because
again.
the actual raw file is already compressed, right?
No.
Yeah, the rules just. Quite heavy added, actually.
Okay. Any more questions or suggestions or? Thank you very much.
You're welcome. So this one back here.
I don't know if it's really on laptop then. So we're using yours, right?
Yes, thank you. Actually, it doesn't matter so much.
So this afternoon, I'm going to. Okay, cool. This afternoon, I'm going to give a talk on what we've been doing in the Proteomics Standards Initiative to look at compression of raw ML data. Some more simple techniques to compress, but now I've been asked to give a demo. I thought the nicest demo would be a bit of some work that we've been doing in our group on the signal processing and more advanced compression and denoising techniques. So here's an example of the results of our approach. So it's a little bit washed out, but you can still see. So in the top left, you have. I should say that most of this I'm going to show is proteomics data. There is a metabolomics data set or lipidomics data set. But there's absolutely nothing in the techniques I'm going to show you that's specific to proteomics. It all deals with raw signal and raw data. So here's a very small section of a proteomics data set, and actually in 2D with MZ against LC. And yeah, this is TOF data. This is fairly low resolution TOF data, but I'll show some higher resolution TOF data later. This is done on the Agilent infodep. So you see these horizontal lines here. This is missing data caused by DDA acquisition, MS2 acquisition of the proteomic. So I guess you don't see that as much or at all in the metabolomics data. We have a single parameter, a bit like the Waters tool. You can choose a low, medium, or high denoising of the data. It also does, as a kind of implicitly, as part of the denoising, it imputes the missing data that you have here. So on a low denoising, and we don't actually, it's not really denoising at all when you have it this low. The aim is just to get a transformation, a representation of the data that imputes everything, but keeps all the structure that you possibly can, including all of the noise structure in the data. But you can be a bit more aggressive if you want to, and go to say this level or even to this level, and hopefully you're going to be keeping most of the interesting signal, but rejecting a lot of the noise. And the aim of this is a fewfold. I mean, it works nicely for compression because we can get 6x compression there, and this is even 236x compression, so it's very tiny, the data set after this. But this also helps centroiding and feature detection. And we're also going to show, the actual demo is going to be on visualization, because this enables very quick visualization of the raw data as well. So I'll briefly give you an idea of what's going on behind the scenes. We treat the data, we fit to the data a bunch of elementary shapes. These Gaussian-looking things, they're B-spline basis functions. Essentially, that's just Gaussians with limited width. We try and fit a small number. We try and choose a small number of these shapes to fit the data. And the more aggressive the parameter you put, the less of these shapes get fitted to the final data. All the others get rejected. As you can see, they're at multiple scales. So you've got very thin ones and some very thick ones to try and estimate the baseline. So the idea is that you select these shapes, and then when you weight the shapes and add them together, you then get a nice smooth depiction, representation of the original data set. Now, I must hasten to add that this is showing it on an XIC, but it all works in 2 dimensions. So the shapes are 2-dimensional. That is purely, these are you can see all the individual shapes, and then when you add these up together, you get that. It's the sum. And the other difference here is that the different colors represent the different widths. So you have the smooth, all the wide ones added together are this red. Yes, so well, actually, so you've got a yellow and a blue here that are the very low frequency ones, then red is higher frequency, and then green on top is the highest. Actually, blue is the highest there. So I got a couple of slides on the theory, but I mean, if you want to talk to me about it afterwards, it's probably better. We use a sparse regression approach, which is essentially the lasso that selects a small number of these shapes. This is a kind of big problem, because big data kind of problem, because we have we start off with a billion or more of these shapes for an LCMS data set, and then we try and select tens of thousands out of these, say, or hundreds of thousands. So it's all built around speed, even though it's not a particularly quick algorithm. Absolutely, it's very quick for processing billions of these shapes. Just slightly more technicality, we assume an underlying Poisson distribution to the data when we fit these shapes. So that's why we don't use the ordinary lasso. There's other algorithm being presented to solve this problem. So I showed you time of flight on the first slide. It also works with the Orbitrap data. Of course, the Orbitrap data is significantly higher in resolution. It's not exactly Poisson distributed, it's more pseudo-Poisson distribution, and we haven't really looked very deeply at the characteristics of the Orbitrap. They have the problems that the baseline has all been subtracted out of the Orbitrap data before you even see it at the instrument level. But essentially, this is just showing you that because we fit these shapes, and because when you add these shapes together, you get a nice smooth surface, that allows us to impute all this missing DDA data as reasonably as we can.
Yeah, that might help also for other instances of missing data.
Mm-hmm. Oh, right, yeah. Yeah. So I've got a little bit later, I can show you this working. This is just a video demo at the moment of the visualization. So one other nice feature is that usually when you want to load up and look at a full data set in 2D, it's gigabytes of data. It takes a long time to load up, pan, zoom. But when we've converted these to these shapes, we can then put the shapes in a tree format, such as R-tree, which is a spatial tree format, and then we can very quickly stream only the shapes that are part of the view that you want to see. So this is just kind of like a prototype demo application for this. It's not exactly feature rich. So you can actually see this is an overview of. It's going a bit quickly, but you can select bits. You can get the spectral and the XIC and zoom in, and it's very quick at doing this. And I'll slow it down a bit later So I'll give you a live demo of this.
Just out of interest, if you were using the record shapes essentially as the further compressor function, how does that compare to the just storing the data as the data?
So you're saying, sorry, say that again?
So you were essentially here using the fitted shapes
Yes.
as like as another view of the same data.
That's right.
And I imagine that's even smaller
Than the raw data.
raw data was just I mean, this is almost like another compression.
Indeed, exactly, yes.
This is like rasterized data.
Yes. So we published this recently for the visualization, but we are now in the process of showing, and exactly what you say, to demonstrate the compression and the compressibility of this the data. So it, of course, depends on how lossy you want to be. The data I'm showing here is at the very lowest denoising level, very little denoising. So we're trying to keep everything we possibly can. And this is about 6 times smaller than the original data. But we won't, we want to develop a compression format with these shapes that also allows quick visualization as well. So it will be still in the R-tree format, but at the moment the R-tree format is very wasteful of space, but this is why we are using HDF5, and we're going to put it in the HDF5 to be automatically compressed. But that's still work in progress.
So a question regarding that compression. So the logic is because you simplify the data by fitting all these lines, and then we also end up with the residual line.
You end up with
So
a
you're
residual.
doing residual, that's the logic in compression, right?
Yes.
But on the other hand, these shapes, they have a kind of semi-parametric form, right?
Yeah.
Can you
They're fully parametric.
full parametric? So have you looked at the difference between reconstructing the model data versus storing the numbers for the parametric models as a compression algorithm?
But we looked at just storing the.
Just storing the values, so you rebuild them with the splines.
Yeah, that's it.
Yes. Okay, so
That's exactly what.
Just like so you've got your modelled spectrum,
Yes.
which you could store at any resolution online. But I'm presuming you just store the coefficients.
We just store the coefficients, and then this is reconstructed from those on the
Each
fly.
time you visualise it, you reconstruct it.
That's right. Yes. Yeah. And it's to say that because these shapes are fully parametric, say we can zoom in as much as we like, so that they're perfectly smooth at any level, particularly in the chromatography dimension there. It's essentially performing an interpolation.
Do you constrain the bits in any way with respect to each shape?
The sparsity is essentially the implicit constraint on that. So the more sparsity you have, the more aggressive it is, the less flexible the surface becomes.
Right, but it's not going to apply any constraint on the
No, it doesn't. No. Of course, the dictionary we use, the B-splines that we start off with, could have some constraint, but we don't. We make sure that the finest level of these B-spline basis functions are much smaller than a peak, so that you will be capturing any shoulders or other bits and bobs if you don't put the shrinkage high.
B-splines are also
They're also metric, yeah. But
I probably you already experimented thinking about other basis functions. I mean, wavelengths.
so yeah, that's an interesting one. So absolutely, actually, the reason we chose B-splines was or this method in general is because we can use any basis functions with this sparse regression method, and in fact we do have some work that we're going to complete. We're going to polish this off first, that models peptides all in one go. But wavelets, and the actual algorithm, we could have wavelets. In fact, there are B-spline wavelets that have nice continuity properties to them. We've recently put in a BBSRC follow-on fund application to create a production level version of this, and we have suggested that we will use wavelets for that. Basically, because yeah, because for purely visualization purpose, the wavelets is going to encode a lot quicker. But for other tasks that we were originally thinking of, like feature detection and stuff, the B-splines are more flexible, allow more flexible bases for demo. And in fact, the next slide just shows, tries to show the benefits of this denoising for feature detection. So this denoising is working, of course, not just on the baseline, but on the peaks themselves. So actually, this software is interfaces with ProteoWizard. It's all it's written in C++, and you can save the denoise data back out to MZML format, so that you can then put it in a package, and it has no idea that it's been denoised. So we did that with Progenesis QI and had a look at the features. And this is an initial validation, but if you can see, we're picking up a lot more features here. Now, if you see it on my laptop, you can actually see these features. So we have visually seen that a lot of these. This is not a spike-in data set or anything that we have like a copper gold standard or silver standard validation on, but we are pretty happy that a lot of these are real features that it's now picking up near the baseline. And then finally for this talk, before I go on to the demo, what we have done and validated is using this denoising tool as part of a fully image-based workflow for differential analysis. So our denoiser, essentially, it converts it to the data sets to images, and then we register or align the images together, a bit like Progenesis does already. But then we work with our collaborator Jeff Morris in Texas, who has a differential expression statistics. Essentially, it's a Bayesian statistics model that works on images, and we can look at the pixel level whether things have changed or not. So here we have a three data sets of one in green against three data sets in magenta. This is a spike-in study. So for each pixel, we can get a probability now that each pixel is differentially expressed above or below a certain fold change. So this is showing you the probability that each pixel is more or less than twofold change. So you've got all these hotspots here already, but you need to do a false discovery rate correction, which we can on that, and that actually comes out with these red contours here as being significantly changed at an FP1%. So I just remind that we're not using any biochemical knowledge at all. So it's coming out with these isotope distributions just by itself.
So for that test, is each pixel done in
So it's I've skipped a bit. In fact, I skipped a lot actually. So to answer your question, all the data sets are wavelet transform, and then the statistics is done in the wavelet domain.
So there is a connection between pixels.
Yeah. Yes, and there's a hyperparameter with the spike slab distribution running across all the wavelet coefficients as well. And then that's just inverse, we just do the inverse wavelet transform, and here's the results of that. And I've now, what I've boxed here are the five features that Progenesis detected. So we're finding ones like here that Progenesis didn't detect, and the box we have here in orange is the one that Progenesis said was different. So we've published that in technical publication, and we're proceeding to look at that on biological data set, on production data. So I'll bring out the application for the visualization. Hope it doesn't crash. When I say hope, it probably will. Sorry?
They were affected.
Yeah, that's the real deal. So I can show you some swath data, and I can show you some lipidomics data. So this is an MS2 from swath data set. It's in fact the swath. It's quite interesting actually. You can tell exactly what swath it is because there's this area of between about 400 and 425, and which has more in it, and that's the precursor range of this swath, basically. Just if I go back to the overview, you see how it's building up the image from all these shapes, and it starts off by streaming the most intense ones first, the most important ones. Because if you still leave it still would take a whole minute or so to actually bring up the whole data set. But actually, it looks as good as you want it within a couple of seconds. So, and when you zoom in, it's pretty quick. You can see it a bit flickering in the background, where it's actually still building up the noise in the background. So that's basically going down to the this is for the visualization. We put it on the minimal.
So when you're zooming into the data, because you're constructing the shapes,
yeah,
are you using always the same degree, or are you kind of upsampling when you're zooming out?
So it's we use the resolution of the viewport of the display actually. So when you zoom out, it's actually binning. Well, it's not sampling. It's actually binning these shapes. So it's basically using that viewport as a two-dimensional histogram and binning it with the shape.
It makes it faster. Zoom out.
Yeah. So that's why. Actually, I'm not sure that it's going to work. Well, that. The bins here are actually, there's more bins now than there is in the original data set. And that's why, you see a little bug, right? That's why we get a smooth profile. Yeah, it's more smooth than the raw data. Yeah, exactly.
Those little dips in the mass trace at the top.
You mean this?
Very small dips where it seems to go negative or below the baseline level in that trace at the top.
Yeah.
Because there's a few bits where it seems to go negative.
It's not negative. It might be because might be because the other bits are slightly positive, but it can't be negative because the algorithm can never go negative. I think that was just aliasing, really.
Or at least it's stretched out.
Yeah, I think it's. Yeah, yeah. I think so. So, we have some more feedback.
Just another question on the rendering, are you using any GL?
But if we do get funded, the new one will actually be a 3D.
If they're not accelerating these, maybe this efficiency.
Yeah, I mean, a lot of the decoding can be put on the GPU, yeah, and done directly. Yeah. Yeah, so this is some. This is it's using your protocol. I think it was done after the network, but I think it's using your protocol. So I guess that's a bunch of lipids. This was good. Good words. So the Orbitrap data, of course, is very high definition, very different. Well, that's it. Any questions? So as I say, this I suppose what I did. The encoding stage is fairly computationally intensive. Actually, I can tell you how computationally intensive it is now, and then at the end of October, at the end of August, it should be quite a bit less. But we're say on the order of a few hours per data set to encode this data. A lot of that actually, a lot of this data that I've shown you has a lot of zeros in it, a lot of areas of nothing. The algorithm is rather dumb at the moment in that it's processing all those areas in the same way as the areas with stuff. So that's why I'm saying we're going to take another iteration of this to reduce that.
So a few hours on the desktop.
On a desktop.
Is it naive to think that this is trivial parallel?
It is trivial, yes. You can well, not so much across a single data set. Of course, you can do lots of data sets. Or you can do tile. You can
parallelize because these splines are, like you said, maybe that's the very wide one.
We do have the very wide ones, but they don't need to be massively wide. You could tile it with a little bit of overlap and then do it that way. So, actually, though, possibly not desktop computer because at the moment it requires quite a lot of memory. So we run this on our server, and to encode a data set takes about 100 gigabytes, 120 gigabytes of memory. If you limit the tiles, then it doesn't.
Sorry, but also if you limit or you go towards the noise,
no, it doesn't. It doesn't. You always start out with all possibilities. And the more denoised you go, the more it rejects, but you still start out with all of them.
Yeah, I wonder whether you could, quite a big change in the model to encourage different levels of scarcity in different areas of the rental space. So, and to search through different combinations.
Yeah, because like I say, it is pretty dumb at the moment in that it's putting these in areas where we've nothing. So we haven't done the optimization to discard all those areas, which for things like orbit data set will actually probably massively increase the performance.
So when you said a couple of hours, does that vary between the time data, the orbit data,
The orbit at the moment, you say the orbit at the moment the orbit track data does take longer because it's higher resolution. So you have to have a lot more of these very small. But it shouldn't. It should actually orbit track data should take less time once we only process the peaks rather than the areas.
Open source.
It's yeah, it's fully open source.
So it's something
It's on GitHub.
you can play with.
Sorry?
It's something you could play with and see.
Yes,
Can you further those and
absolutely. We are looking in that direction ourselves. We're working with a Hartree Centre, which is a supercomputing centre in Desbury, to look at parallelization.
I mean, because institutions like this one, there are large clusters, not very powerful machines, but just a lot of nodes.
Yeah.
It's a bit different. So adapting into this type of cloud environment.
Oh yeah, definitely. Yeah, interesting.
So shall we make a question? Yeah, sorry. The way the imputation method is used, for example, you have this line which goes with signal and node, right? The one that very first images. So
Yes, that's right.
So you just not reconstructing the noise, you're using the noise but also the signal, right?
Yeah. Well, it's doing both really. It depends on how much denoising you've done it on. So it's estimating the shapes from the data, and then it's just extrapolating where there wasn't any data based on the shapes that it's estimating.
This is pre-splicing.
Sorry?
Before doing this B-splicing or?
No, this is
This is actual B-splicing.
this is the B spline. Yeah, that's contrast. The B splines, they're selected, and then when you do the reconstruction, it's a continuous surface. So it implicitly gives you the areas where there weren't any data to begin with.
That's quite nice. So there's a lot of well, there are different reasons why there are a lot of the sparsity in different data sets to be biological to instrumentation to occupy to. But I don't think there's any good method that hopefully the different source of or reasons for sparsity. This is very nice. And by itself, I think it's quite nice to be able to use.
And I suppose so that swath data has a huge amount of missing data because it's only taking one spectra and then missing out the next 32 and then coming back. So we're doing the interpolation across that, which is what you saw when
it's still subject to the same uncertainties with interpolation that we would have.
Yeah, oh yeah, absolutely, absolutely. So if you've only got four, I guess the problem there is that if you've only got 4 or 5 data points across the chromatogram, when you're doing the interpolation, you're kind of assuming that those 4 or 5 are very clean, because it's just fitting those points together basically. You can do a little bit of smoothing, but button for all the data. So it's not exactly correct for the Orbitrap data, but it works. Yeah.
Does the job.
Yeah. Yeah, indeed, yeah. So I'm not showing them now, but I do have some slides where we use prior knowledge of peptide isotope distributions to extract peptide features directly. But that's prototype code at the moment. We originally looked at these on single spectrum, and then now we've scaled it up so that it will get more LCMS data sets in 2D. So we've got this, and then the next stage is to port over all the old code which did the peptide isotope distribution, and also potentially metabolite isotope distributions too, although they're considerably more variable.
How big is the peptide?
The peptide library we use is Uniprot. But we have a learning method that summarizes the range of isotope distributions in Uniprot.
Don't have an equivalent of the Uniprot,
Sorry?
you don't have an equivalent of the Uniprot.
Right. Yeah, if
It's kind of all over the
talk
place.
to Andres about this, because this is what he's interested in. Yeah. Yeah.
There's no more questions.
I think we can continue this discussion.
Sorry? Schedule.
Solutions for direct diffusion.
Yeah. I mean, yes, making sure
Yeah, but it's basically the concept.
Well, it would be better coffee, Chris.
Yeah, it would be better coffee, yeah.
So we.
It's live.
But I really think WebGL is really cool.
All right.
But at least, Chris, you can say it's a better coffee.
It's a better coffee, yeah.
It's a value.
potentially we can tailor it, and it would actually have better result on knowing that it's a concept.
Yeah.
Because we don't need to model variation.
Yeah.
We can just say we expect it to be a concept when we do the fitness.
Yeah. I can send you from later.
Okay.
If they're interested.
We look at it. I have collaborated in Liverpool that's top down.
Right.
So I haven't had any data. Yeah.
Yeah.
So
Thank you.
well, no, I'm going to try and find that.
It's really good.
Actually, there's no one.
Actually, it's about this here. So you want to have a meeting that?
Yeah, about it's for the allergy, not like an everyday stuff.
Unbelievable.
Yeah.
Yes. So I think so.
We will get access to that. EPI network.
Any?
And we want to let people know like about regarding the unions dinner.
Yeah.
CBI paying for that?
I don't know, that's Chris and the rest to decide. I don't know. I would assume so. So we need to chase Chris on that specific. Not a delivery. Not a delivery.
Let me put this back.
Yep. Well, I don't know if let's make work. See if I can access.
Are you able to log into the cluster from there? Yeah. Because remember, when this is a training. Yep. Actually,
I backed it.
still connected. When I connect the gate, yeah, I can shut this down, and I can close it, and I can take it home, and we can open it again, and it just reconnects. But that's the gate.
This is just
So you are really connected.
network.
Next week.
Same line.
And the problem is right.
That's different certificates. No, that's different certificates in Africa. And they so very silent. So semantic issues very silent. Certificates. They haven't changed.
Like saying,
It's not
had
like
a
it's like
max.
so the-
None of these connections were new. Were there. Still. Attribute and deal with this.
okay.
Objects. And I added a few, I'm not sure which one. That is one connection timeout.
Yeah.
I will cover this. And I also add maximum connection we use like connection, which means connection can be only used 50 times.
That really means
The time is how long?
what are people about it? So this is like
I think the default is 0 and it's there's no can be used.
that's absolutely working quite well with the local agreements and campus server and that sort of thing. It's really big to get it tested.
Susie would love to try that.
It's just it's actually one of the just I mean I want to cast it up and yeah.
So this would be collecting new song. Just analysis.
When I created
But it's very
Sorry?
It just popped up saying this is this was the
Okay, so we've got like half an hour we're discussing what to do, but I think the discussions is the best thing if we can steer a kind of discussion on what you saw and heard in the morning, and generally what do you think, how do you see it in, it's one of those questions, predict the future in 5 years, 10 years time about data storing, data lossy versus lossless, compression, different compression. There are nice formats, real format, I guess. We talked quite a lot about SD5, and we got better formats and so they were XML based. You probably will cover that
this afternoon.
this afternoon.
Yeah.
We only have half an hour, so
Okay.
but there's a good spectrum of data producers, data generators, data storing, data compression. So I just want to see if you can know how do you see that?
I mean, what we've been thinking is that you can do this transformation to these basis functions, what I showed earlier. Obviously, we still want to have lossless or almost lossless archival of the data, but you've got the residual, meaning the difference between the fit of what we showed you and the original data, and you can store that in a HDF5 file with these coefficients. So you can do all the visualization. Our plan was to have the visualization working across the internet. We haven't quite got that far yet. But also you could reconstruct exactly the raw data if you take the coefficients and the residuals as well. And the residuals should be very good, should compress reasonably well themselves. A lot more if you do statistically lossless rather than lossless compression on those residuals.
That's by any format, for example.
Sorry?
HDF5 or
Well, it would have. See that's the thing. I mean, it would have to be HDF5 because we really, if you want to do visualization of this data, you have to have very good random access capabilities in your format. And MZML only has random access at the spectrum level, whereas HDF5 it handles it all for you. It has a lovely caching layer as well as the. So if you random access a few points in the same location, it will only get that one block out and cache it. So it has all that lovely layer to it.
I was going to say, maybe a good background of what these defined is, so and this.
Yeah. Okay. So HDF5 is a format for numerical data that was created a long time ago in the National Center for Supercomputing Applications in '87, and it's been adopted by NASA since the 1990s. It's a binary format, but it's self-describing. It's open source, self-describing, meaning that you can just use the tools to interrogate what data types are in there and what the formats are in and everything. It's called hierarchical because it's a group structure, a bit like XML, in that you can have folders inside the HDF5 and then data sets with attributes in that. Completely free of charge. It's completely portable. It's written in C++. There's actually a pure Java version if you use NetCDF. NetCDF4 uses HDF5 under the hood. So, and I say it's very fast for random access because it has all this layer of caching, and it also uses B trees and such like to store the different chunks of data. It's multi-thread compatible, and it's used very much for storing large data sets that you do parallel processing. So I think the main thing is that it's almost de facto for certain geological applications using it. So there's a big user base here.
I would look up in terms of user base that certain languages like Python now, which are very popular in data analysis and data science, are using HDF5 as part of their everyday use. So you have pandas in Python uses HDF5. It's happening also in R. It's becoming such a standardized format, community-wise data analysis, that it's no longer a weird thing that you have to download. Or it's community-wise is getting a lot of traction. PyTables is even a database built on HDF5 because that's one of the old features in HDF5 that enable you to do some neat database engine things. So, but as I was saying, community-wise, even Julia languages, they are for data analysis. Pretty much everything reads HDF5.
The problem is, I guess, adoption of such a, because a lot of things are commercial, right? Or developed within, how difficult is the changing this from existing?
So the talk I'm going to give this afternoon is going to suggest an easy way.
Moving on.
Because obviously there's been a large investment in the XML schema and everything. And mapping to HDF5 isn't, there are some gotchas there, which is why MZ5 has a database style mapping rather than a hierarchical mapping to HDF5. Because, for instance, any group or indeed any object in HDF5 is a minimum of 4K in size. So if you mapped XML directly to HDF5, you get enormous data sets because every single node would be at least 4K in size. So there's hurdles that way. So our proposition is just to store the metadata XML, the MZML metadata that's in XML format inside of HDF5. That gives you the advantage of it being compressed by HDF5, and then you just extract the binary that's currently base 64 encoded in the MZML, and you just store that as native HDF5 data sets side by side with the XML data. So in that case, if you want to read the XML, you just need to grab the XML which is encapsulated in HDF5. You want to read the data set, it's quite simple to do that. So that would be a simple simple extension. But I know in the PSI, at least for the actual MZML standard, that there's some feeling that even that is too much of a change.
from a lazy programmer point of view, I would say it's actually quite easy to convert a lot of things to that. I would say it's a no-brainer. It's more about community thinking what you really want and settling up for how you want to have it. And it's more defining what you want to stick to. I mean, there's lots of options with more and just trade-offs.
So again, with how much will be the compression? I know it's very difficult to say in general terms, but from an MCML file to a proposal that you have made.
You mean
Because it's very-
you mean the HDF?
Yes.
Not talking about what I talked
Yeah,
about.
no.
Just talking
Basically, I want to what you said. What would be the difference in size? How you-
we've got a little bit here. Because I haven't talked yet about NumPress, which was a paper that came out last year, which is just some simple predictive compression for the binary part of MZ. But that doesn't include compressing the metadata.
Yeah.
So when you have everything together, what are we talking about?
So it's actually around 80% of the size of the initial value out in the month.
Which percentage? Is it?
About 80% size of the manufacturer.
Which
Because that was the
okay. So it was slightly smaller than
and the ML inflated almost 2.5 size. And the HDF5 you're actually getting a bit smaller file than the original.
NumPress is not lossless, but it truncates at 6 or 6 decimal place. So I think when at the PSI meeting, everybody was happy with that. The dissension that was dangerous.
But also the very good bit of HDF5 is that it's not only about compression, it's also data about data, especially if you have huge experiments and you are working on your desktop machine. For XML forms, you have to load them in memory before you actually can start accessing data. HDF5 you can access the parts and the data without feeding in the computer. So it's also efficient for the software pipeline.
Yes, this is the really big advantage in indexes as well.
Yeah. And there's potentially another big advantage. So as I said, that NetCDF4 implements HDF5 under the hood. It's a subset of HDF5, and honestly, you don't need to use the rest of HDF5. We could be talking about NetCDF4 rather than HDF5 to store the data in. One of the advantages is that their library for reading and writing NetCDF4 includes reading and writing over HTTP. So you can if you have your web server set up with the forget what the Apache module is. It'll come back to me. But you can just access just the library will take in a URL rather than a file name, and you can just access even just part of a data set, an area of a data set, or whatever, directly from that URL, which may be good for the repository access.
Moving data.
What do you think of the study that follows versus MCDB?
MCDB. Okay. Yes. So.
So MCDB is a format that was developed recently by.
So that's the other. So that's developed in France,
Yes.
Strasbourg,
Yes.
by David Busey. So that's an SQL database, basically. That's the other option, rather than HDF5, and that's specifically, well, actually, we discussed it quite a lot, and the MZDB is a SQLite database format, but also because it's an SQL schema, they also have a backend for a Postgres database which they use for the LIMS system. So that's very nice in terms of one direction that Andy Jones is very keen on, is developing that format further with MZ QuantML and MZ IdentityML, and having a kind of mini LIMS system based around the MZDB format. I'm not so sure whether that's a great interchange or archival format. It's limited on compression. In fact, for instance, if you're talking about SQLite, it can't. There are extensions to compress, but they're commercial extensions, where each person who reads the database has to have the license. And in general, their approach wasn't aimed towards compression at all. So the SQLite representation is not is for quick data access. It's not for space.
What's the license?
So the license, off the top of my memory, I can't specify exactly. SQLite's fine for it's free to use. It's if you want to either compress or encrypt the database that you need a special license. But that's not. But that's just for that's. I don't think that there's been any tests to see how much it actually compresses the database, because it also depends on how the information, the schema you put the data in the database. And so I just don't think it would be flexible enough to get the same kind of. I should add, important, that in terms of the binary data, the way they do that is that they group together small chunks of this data. So it's like 5 MZ segments or strips of the data. They put each one into a. They essentially have each row in the database has a binary, a blob or a binary, and then they're storing small chunks, and then they index these chunks by the R-tree spatial index, like we do, but it's on these chunks of data. And they would have to compress within these small chunks, which he did say doesn't compress very well.
What are these chunks? I mean,
they're chunks of raw data.
Just
arbitrary rectangles of MZ retention line pairs.
Because it's especially a lot of swap, right?
So for the swap protocol, they actually have an index by precursor. So they've done some processing which allows them to quickly cluster precursor with the MS2 data and allows them to visualize that quickly as well. So yeah, so in summary, it looks like a nice format for query. Obviously, for querying, it's got a lot of strengths to it. So if you're querying across a huge database of all the metadata of many different studies, it looks very nice. But that seems to me to be complementary to a HDF5 approach for actually storing the raw data.
It's part of what I've been playing with is actually combinations of SQL for the metadata and then using the coordinate-based system to store the data on HDF5. So you can even specify the compression of the binary data with HDF5. And then uses the SQL query language to have all that really nice select all the data that I want within certain categories. And then because it's coordinate based, you can actually go and fetch from the raw data all the spectrum that you want and log it onto objects or whatever you want. So I think it's a really good combination.
I agree. That works. That's a good combination.
Especially with SQLite and other things that are so open source easy if you even have it. I'll be interested to do a couple of small gadgets, maybe even interface UIs and try to come up with a small go to the database, parse it into small SQL data, plus HDF5 and things, simple objects. So you can almost download a usable data set, not just the data net. That's probably my experience.
So in the proteomics community, if I understand it correctly, there was a relatively good adoption of open data formats developed by the community with vendors eventually worldwide. Is that correct? Or?
Yeah, well, you mean with the MZML?
Yeah, I guess that. Yeah.
Yeah, so I think there's very good adoption amongst vendors and the community of the formats or the MZML, and I know that the MZ1ML and MZ-IdentML and MZ-Tab are not mature, but they seem to be going forward quite nicely. I guess to say one thing that we see they've been thinking about compression as an extension to the standard, but also perhaps realizing that the standards are all interchange formats, and it's not the same. Interchange is not, there's not the same requirements on interchange as there would be for archival or back-end format for querying or whatever.
So is the situation still that vendors are using their internal formats and then only offer export capabilities?
I think so.
Certainly the way it works currently with those applications. Would you be willing to comment on everything about Metabolomics? So there's no reason why we should get to the same situation in Metabolomics. Absolutely, we're developing. We go on with those and then probably show is the way of moving forward with the vendors.
As we were discussing in these meetings that the joining forces of the Metabolomics proteomics and getting with industry more engaged. Because that engagement a couple of years ago was very strong. But the way I understood from participating in the DSI meeting, that it kind of declined in a way that not intentional, but by discussions and then sort of the idea to try to re-engage again. And
At all of the meetings seem to be for the same, trying to address the same problem. How about working on this Metabolomics? People that's the notion of fair data, so something that's findable, accessible, interoperable, reusable, and reproducible. I don't think any application is unique to the rest. And the vendors, it's in their best interest to work with communities rather than.
So
If you have waters is very good for that. There are others that are not so good.
Yeah, well, it works in a good relationship with the
Yeah,
rest of the vendors.
there are others that are
work
not.
closely with them, and I think maybe that has been part of the success of that relationship. But Leonard's involved in that space.
I think the community pressure, not pressure, but request, because that's what drives you have to have a request from your user, otherwise you're not investing. And that's the logic that I understood that has to have some sort of financial basis, rather than just being at the bottom. But things like genome centers that have now kind of a way to have data, issues related to data, also coming soon.
So if I understand you correctly, then the situation will be that we're moving towards a situation where we have the vendor formats to be used probably. I think you're always going to have them on the instruments exactly, and probably also be used by the data producing centers in their direct data analysis. Then we'll have the data exchange formats such as MZML, and then we are in need of a high performance data format for
and as well as for, let's say, public computation, for using open methods on open data that are performing well in HPC scenarios.
And I think proteomics is in need of exactly the same thing. So if it's something that can be linked up with proteomics as well, that would be great. My understanding that MZML has got good take up in metabolomics now, amongst all the vendors.
But it's the same library.
It's the same,
It's
yeah.
doesn't it?
Yeah.
The same protein research convert from proteomics to anything. The only thing you added was sort of the GC, which I know.
Oh, okay.
So GC wasn't supported. It's same. And now, but then again, GC is a subset of management, and now that's in place. So even GC wasn't supported. There's no need for GC. Now,
And the consensus is to look into MZCAP for metabolomics rather than MZ
that just was a compromise of time and resources and expertise. So compared to proteomics, the expertise in metabolomics is no less much. So without the proteomics meeting with 30 people sitting active in metabolomics is already in the workshop in San Francisco. It was for the first time again. And again, you were there, half of you were proteomics people coming to the same one. So it just, we tried, said, well, no, we tried.
Yeah, he turns very keen to bring in.
The pickup was so slow to engage. It's several times tried. The only successful workshop we had was in which we had a group of people, and yeah, half of them were people there, but just the momentum is so slow. That's why investing in IdenTML would have been very expensive. Tab is so simple compared to complexity of the response and ident. Still hoping to one of the fundings to get still carry on. But not even
there is no reason why he will be to provide the data in performance in archives. Yeah, accessibility, you can use that for reuse, computation, whatever. We just haven't got enough manpower to do it all. We need to write converters and so on. So far, they don't exist.
It's the same level of model, and now I'm kind of accepting it. So you know, the huge form of small changes. More like, say,
But there is a system, there's a system to capture this information in place by just getting the right people. And they're finding the right, showing the right channel. So that's very accommodating. I think I would say the problem was more from the technology community. Not putting say, oh, there's a problem, I'm not going to use it, or there's a problem, feedback to the maintainers. It's a very nice system, and you want to describe the system even better than I do.
So, well, the way we work is that, well, there is a, so it was more active before because it was very, very active for some time, because when the formats were developed for the first time, it was when everyone was very enthusiastic, and is where the actual big lot of the work was done. Now, since the standards are more or less stable, well, there is less demand, but still there is traffic on the mailing list. There are several mailing lists that work as a subscribe to. As soon as they're interested in something concrete, there is a possibility just organize a phone call and try to push things forward. And well, let's talk about this MCPAC meeting that we have been doing last year. And well, just we are open. I mean, we have a lot of people are open to go and help us out. We also have the annual meeting of the PSI that we also have been there a few times. That is also used to discuss this in person. So there are ways to do it. We still have some funding for those people, for instance. But, a couple of more years. So the attendance to the meeting is free. But you have to, so you don't have to pay any registration if you need to cover your trip and accommodation expenses. And it's always also good to have new blood because I personally have been involved in many things, but also other people have been involved in many things. Sometimes we're happy to help, but not so happy to leave because we have been involved and it's not our core interest area. So that's, but things like MCTA, for instance, I think that honestly we did for Metabolomics, it wouldn't be so complicated to do. It would be actually, I think, relatively easy because we did already the framework. I think it was a difficult part. We was extended for, I think it's not that complex. But again, then the difficult part is to get the adoption and to do the converters, all that takes many years, but we have to start somewhere.
So the next meeting, if you can put your calendars, the next PSI meeting is 18th of April to 20th is in Belgium. So Ralph,
Good.
Michael, everyone else?
Say that again.
18th to 20th of April 2016. I think 10.
Good.
What group is beyond there?
If we can get this density of metabolism decline, can you break one out? Anyone who wants this again, that's what I'm trying to say is it's more difficult. Any industry is there as well. What is always setting this present.
Yes,
as
has been several times.
Yes. So empty tactics then would that still be a single version of empty tactics which just covers both metabolomics and programming, or will you have two different flavors?
For that, it's a good question. The ideal way to do it would be to do a core that would be applicable to both, and then to do like things that would be like specific. So when we did it originally, we of course thought about proteomics. We included an extra section for small molecules, but it's very rudimentary. It's just to be able to record something, but we cannot get too much into the details. So that's why we probably need to have at least 2 or 3 different sections to look into it. Then this year we have interest from people working like omics that actually themselves they did extension that they did by themselves. In my opinion, there were things that could be improved. But anyway, it's just that there are a lot of interest. But yeah, this work that needs to be done. And I think again the difficult part for us to do the framework. We also have the libraries that or the many software tools can be repurposed as we have mentioned before. So just there needs to be the will. And yeah, it's a lot of work that sometimes is not very nice to do because it's a lot of back and forth with people with different opinions, and that needs to be done sooner or later.
The basics of metabolomics data set that evidential of how we come up with this event. So we can do that by using the existing parameters example. But the nice thing about it is the same thing. For example, you can say that which data we play, how do I match it, what was the routine, and how is it going. If that's the hard part. Hard partially relies on the community group. Yeah. So I guess Rick came back just right time because because that's falls in the domain of the development society and going by the task groups that we try to do. So we look at set up how to enrich it by not just saying that these are a number and a means and value, and actually use database of how do I ID them, how do I know how confident am I them. So capturing all this method is complex. But partly is now in society, and thing is there as well. So to be able to come with that accepted community-wide
There is also
agreement, and then that implementation of that agreement is, because if we do it ourselves, for example, then it's not necessarily people have to.
Yes.
no, but someone has to lead it and needs to propose the main things, and then there are things that will be accepted by everyone, other things that will be discussed. Yeah, that's yes. It's always someone who does most of the work.
I was just about to say, we've got the leaders of the two relevant task groups.
That's right.
It's like our ID and data standards. There we are.
But if it goes, somehow it's on our court. So.
Yeah.
You're right, yes.
It's sort of part of the job. You take a lot of main discussions. You go there and settlements. So rather than saying that which one's the best, but they will come to the practical side of these things, how to practically do and discuss the order of stuff. But the fact that reporting and being
There is also this group that is led by Henning and by Oliver Torvaha, this computational mass spectrometry group that is now part of UFO, the Metabolomics Society, and also ISMB, I think. That would be another way to try to channel things.
Stefan Neumann is the person who information is now the metabolic computational micrometry. Stefan is another guy I've got City Go. It's not open. So two of them are so in terms of people power, it's been covered. I think that it was very active. And I think the workshop was yeah, San Francisco, organized by them. So I guess it's one thing.
There's a bit I think when we went to Tübingen last year, that day was very fruitful, but somehow the whole thing wouldn't progress afterwards.
Energy barrier to go over it is this.
For me, I was in the MC app.
Yeah, you were there as well.
I thought the discussions were very interesting. It was not really my field of expertise, but I thought the right people were really good. But I was searching for like a reason for to start using the MC app. Like, what is the added value for our lab to start investing in MC app? Same as why should I start bringing all my files to ML or XML or new formats come out, especially for a production lab. You should have a good reason to start.
Yes. Yeah.
Is that something you can, like, why?
So one simple reason, or I don't know, reason, I can speak from the point of view of MC Identity, which has been going on for a few years in proteomics, and actually last year we noticed that it was more widely adopted. So you can get well, apart from the typical reason of exchanging data with people using different platforms, but you can also do increase more people people can do visualization tools that are applicable to you don't have to do a lot of converters for the same thing. Well, there is a typical issue that we all know. Visualization software, but of course there needs to be adoption. It's a typical problem of chicken and egg. Do you decide that there is enough adoption for you to invest in doing the conversion of the software? The CTAR is not in that stage.
So another problem with that point of view is the same issue. If I give an Excel file and state the sharing, I mean, reviews that it has some value that you don't know where they come from, it has some ID that you don't know how they do it. It probably, as an item, it works, and that happens not. Because from raw data to end data, there is endless paths that you can take. But at least the idea would be to document which path I took to get to this point. The chance of going from A to B is at A to Z is a lot more because there is a clear, more informative than just saying I've shared an Excel file with somebody that are obviously accepted and so on. So the added value of this is traceability of takeovers, the tablets that are identified. But then again, reporting that scale is hard work and it's not trivial as well. It requires a lot of these things. So that's why these things should not be done by hand. It should be done by software. People that are often a software user. So if you use a package and use the raw data and use the method and point Z, you just have to take those into account and how do I get from A to Z. Input that into a nice readable format and expect the exchange. Because by hand you really can't generate that. You think most of the implementation is on the software. That's why mine was there, OpenMS was there. But they were mainly the guys who actually doing that behind the packaging. That's what happened there. At least not all of the criteria, but anything is better than nothing.
If I will have to sell this to the people in the lab, especially responsible for the lab, I would have a pretty hard time. They have their own procedure set up to be able to trace back how you got 2-year data. They deliver it, they have to invest more. If there would be rules around even vendors would also have the ability to make machinery comparable and better.
Well, I would say it's very difficult. I know because one of the issues, many people use multiple tools. Most pipelines, people using 3 or 4 different packages that run specific part of these things. So that interoperability is very to say, I import this and the other one can be done to do the rest. But when it comes down to simple form text space, small chance. But
I think a perfect algorithm or tool would be the obviously start using another format to be perfect.
somehow maybe can show you from the pipeline, which is referring to here's your answer.
Okay, sorry, I missed that.
Reza asked how many pipelines are very close to on average, which you said, and it's only maybe in best case scenario you have one programming language, and then language are different packages. So always able to go to even if there is a
Just example, I think.
I get you. So language studies are wide. I mean, in there, like an R. Statistics apply,
You don't think it's really statistics.
even in MATLAB, so tool functions, which is kind of disadvantage, like the way.
These are difficult. I mean, Jay, how many countries do you use for your?
6, like John, pretty much everything that you just said. We bounce to whatever's most appropriate for the hand. Best way to annotate that is challenge.
Is there a way to keep track of what steps goes about on a pilot line?
I think that we personally workflows. It is recorded when you monitor the data and where you want the problems are, etc. You can share it with groups and so that's and it's the way that people really where our using scripts, how still assembly a different scripting language allow the process. That's straightforward again. Straightforward, right? Which happens with this right place.
It's standardized.
It's a difficult question.
Just before we start your questions, who's staying overnight until tomorrow? 6 people. Excellent. Thank you. We'll be running mainly and red line.
Is there a process? It's been it's in there, what that means, and cancelled.
There is nothing.
Okay, agenda is that. So we added to the old coming to the red line.
Yeah. Pablo?
Yeah.
You want to join for it?
No.
Yes. I think they upgraded the modem. Are you going to ask? Yeah. Yeah. Are you really drunk? Yes.
I'll say it's that long.
It's not a big film in space. Probably maybe just not but in terms of protection, we should 8% is
Lunch is ready.
So, okay, you buffet lunch. Maybe I need one already giving me everything. So.
I get that some slowly.
Yeah. I thought that's a new version of that.
Space. Simple pressure. It should be adding. It's going to be lossless because it's throwing away zeros on the right. To protein wizard. And then it comes out as flows, which is so much space on the ground.
there was no
say that it's change.
No, not at all.
So Jake, did it crash miserably or?
No, well, Fix is finished.
Slides?
Fix is hit by
One, just two. Make one. Like casting, a new compression already.
Yeah.
Oh, cool. Yeah. So which term do you want to
I think it's off.
You don't know what's up. Then
Because I got here. It is, it's search,
yeah, let me see all the whole form.
only the 7.
Research file name and see all the service.
Reality could be anything. Or it's especially.
So what's the server again?
API.
IP.
So what I have is typecasting will have to destroy these labels. That's pretty much just add bits on the right. So if you put 0
So-
PS, it means that it's just add. And because what happens is
Java?
Yeah, 1, 3, 5, 1, 6, 0. I use it to make a cheap compression. Yeah. So because I put 0, I'm not removing it. So this was
This one, then that's the.
But it's just check that whole
No, see, maybe there is both and indexing. It gets a different.
Yeah.
Sorry, indexing.
That's the one.
But
Oh, we don't have any logs anymore anyway. Oh, it's better than that than the product. The logging. The logging in production is probably non-existent.
I was able to find audio to this back I was trying to read it before
see, so this one.
actually because he was
Logged in. It's a private, non-private flag default set. What's the default? Oh yeah,
Comes
because
here as a
you
public.
function as a public. Not existing structure.
Okay, then it must be.
Oh.
two girls come both for some for 60, and then went on to the separate parts, one on the part, the little part, parts, and the other one on cycling. I was studying. Literally, it was that far away.
Yeah, there is separate texting lanes. Yes.
Yeah. Korea. So, let's see. So yeah, I think still. No, that's if you have another license, because you might have lost it and then you buy another one. That's a problem. I have it as a problem. Okay. I have some bug on my part. I have some half. I never thought about the effect of that.
Yeah.
No, it's because we have had a feature all along.
Yeah.
That's because I have
That's why he's number 1.
So that's why.
Yeah, that's fine. Yeah, he leads into that. Or maybe only consumer.
No, you're not. That's a very good point.
Okay.
Well, yes, I can't find Stefan Neumann. Okay, well, I'll prioritize that because I added Emmanuel as well.
As a user, yeah.
You fix the new version, but I'll fix the production version. So the two other existing feeds.
Yeah, my new version is almost back to string again.
Okay.
Yeah.
Okay. I messed with my VPN and I'm not on network care, so I have to wait until I'm back to
Yeah, and work exactly related. Yeah, so now
Yeah, no, we sent out emails so people can come and take what's left.
The universities with students.
Just as you said,
Yes, plug in. Yeah, but no, it doesn't. Yeah, they just do. Standard way of enforcing it off.
So that was kind of the whole width and the whole size.
Are you do we need to stop the sessions with this is the morning session, right?
Yes. Is it still being? Can you go to the browser? On this browser?
Yes.
speed things up.
No, I was not saying.
Oh, you're having a single double. You need a 2-minute break. Don't break.
Yeah.
And the old one? No. Yes.
So, can you see the screen now? Yeah. Thank you. Is anyone else online? Just wondering how many people are online.
I didn't think that.
Okay, so I guess we can start the evening. So we had a very good workshop in the morning. Thanks for people who are online. And a lot of things to discuss, especially HDF5, but we have 2 more people who will discuss it in more detail further. And maybe more about 3 o'clock, there are more representatives from other companies as well. presenting their part. There's a lot of questions, maybe you can ask them directly or for their opinion or things or in the afternoon. So I guess first person here would be guy from EBI, make sure his point of view on things. Yeah, should be.
Yeah.
Great. Well, thanks very much for the opportunity to speak. We touched a few of the things I'm going to raise actually already yesterday. I'm just going to tell a story about what we've done in the sequencing world in terms of compression. I'll mention a little bit about the method itself, but it's not quite so relevant. I think it's more the social things and the delivery of a technology to a group of people in a broad community that will use it in a way that helps them to deal with this big data challenge. So several years ago, so back in sort of 2007, 2008, we were in this position. We're dealing with sequence data. This is the plot that Christoph showed yesterday. And we saw this very rapid growth on a log scale. So this is exponential growth, which is challenging for all sorts of reasons. So we started to get concerned about this. We need to do something, actually talk about compression. The reason for the growth in our case was in part because of uptake. So we had this wave in the sort of mid-2000s. We had this wave of exciting new technologies in the DNA sequencing world. And actually one of the manufacturers, Illumina, a few years after that came to dominate. And it was a very aggressively driven advance over several years in the technology. So we had people with access to the technology that hadn't had it before. The technology itself was so every year you could do a lot more, you could produce a lot more data than you could the year before. So there are a number of components to this very rapid growth. But what we needed, of course, was a way of thinking about how we deal with the storage. So we run a data repository, so we have storage issues. How we reduce the footprint. But also, of course, this affects the network, the internal network. It affects the kind of data structures you use in memory when you're computing on data. It affects all sorts of different aspects of our operation here. And of course, it affects people. So we're driven really by thinking about storage and the impact on storage, but actually this has broader implications. So the starting point for us, and I'll come back to definitions of raw data, but this was the data item that we were trying to deal with. This is a FastQ sequence read, or something like a sequence read from the dominant Illumina platform. So it's a set of bases, so you have 4 letters, and then you have a set of numerics, and these numerics represent points, their scores, their quality scores, for addition that they're aligned to. So these give you some confidence or some understanding of the confidence you should have in terms of the basic position. And so the thing with sequencing is you get lots and lots and lots of these, and they're very short, they're very fragmented. To sequence a chromosome, you have to break lots of tiny pieces. You have to generate lots of these, and you have to reconstruct them through the assembly process. And they're flawed, they're short. You don't really want short reads. What you want is one big long read, and they're inaccurate. They introduce error. The dominant method, the dominant application of sequencing back in 2007, 2008, and probably still now, is resequencing, where you're taking variations, so genetic variants within a population, and you're resequencing them, and you're comparing the reads and the sequences you get from the variants to the reference in some way. So it's very much a reference-based system, and that lends itself to the model that we use for compression. You can't actually see the top of it.
There is a top of the screen all the screen down or something.
Is it on? Yeah.
So it just has to type it.
Oh, it's down here. Okay, that's fine. Actually, there probably isn't great information content in the title. So anyway, so we have a reference-based model. So this is how I'm not going to say too much about it, but this is how the compression itself works. In much of the processing of these reads, an early step is to take the reads and to map them and align them against the reference chromosome. And so this is a process that's happening anywhere. There are lots of tools for doing this, and people understand disagree, people understand the challenge that you have with this. So in our compression model, what we do is we take the reads, we align them against the reference, we order them in that alignment, and all we need to do, so when they agree with the reference, we don't actually need to store that information again because we have the reference. We can reconstruct the sequence. When they disagree with the reference, well, we need to encode the base that the position disagrees. But we can come up with a scheme very quickly where actually, if you have these largely concordant, aligned and ordered reads, you only need to store the start position, the length of each of the reads. With some of the protocols, the lengths are consistent anyway, and the position and the nature of any difference. And if you've done that, then you have the reference. Then you can completely reconstruct faithfully the sequence in your reads. So this is so for the read part, this is a lossless method. Now so we don't store in the method we have. We don't store start positions as literal values on the coordinate space on a chromosome. This runs to hundreds of thousands, a scale of hundreds of thousands. We store a relative position, so there'll be a delta between here and here. So you get a small number, a small distribution. It's much more compressible. And then when we start to store letters, we have a small dictionary. So what we actually do, rather than redeveloping the core compression algorithms underneath what we're using, we really structure the data in a way that fits the compression algorithms better. So the method that we have, that we've developed now, actually uses a combination of dictionary-based and run-length encoding methods. But it's really reusing existing methods and structuring in a way that lends it to better compression. So it's quite a straightforward method, and we back in 2011 we wrote some code to explore how this works, and we were delighted with the performance of it. And this was a proof of principle, so the engineering work started. I'll come back to the engineering work started after this. But we found something that we could work with. So immediately we had quite significant 3.5 to 100 times compression over the existing formats, so that's an immediate reduction of the footprint on disk. But there's a really important characteristic of this. And if you look at the relationship between the compressibility, so the final disk, the reduction you get in disk footprint, with read length and the density. So read length is the length of the reads that come off your platform, and the density is the number of reads, is the coverage for any position in the reads. Now, if you look, so on this one, this is just one of the plots from one of the figures from the paper. This is a bits per base scale, so it's a log scale. So we tend to measure compression in bits per base, and bits to take up per base of reads sequencing per base in your read set. And so down here we have greater compression, up here we have lower footprint, we have higher footprint. And then the different colors represent the different read lengths. So this is 25, 50, 100, 200, 400. And then along the x-axis we've got the density. So this is 10 times coverage on average in each position, 20, 30, 40. And what you see is, well, as you increase coverage, whatever your read length, you always decrease on this plot. So you always get better at compressing. So the read lengths increase, compressing. And that makes sense because you're only storing the starts, the differences, and the finishes. So there's less of that to store on average. If you look at read lengths, then as you get longer, then you see also you drop down on this plot, so you get better at compressing. And actually, that's almost an exponential relationship. So the great thing here is that what the vendors are constantly pushing at, because of the flawed metric seams, they're pushing at longer reads. Longer reads are seen to be more valuable. That's what the technology is driven towards. And higher coverage, more data points per unit sample you put into the machine. So these two characteristics are things that the manufacturers just drive out naturally. So we see big advances in these over time. Both of these play in fantastically into the compression scheme, because it means that as time goes on and data grow, you get increasingly good at it. You don't just do a footprint reduction, you get increasingly good at compressing. That's increasing with an increasing rate. So this means that when you see those exponential growth, you sort of change the rate of that. In practice, there are challenges with that. But in principle, you can actually deflect these very rapid growths, and you can reduce or increase your doubling time for exponential. So that's really interesting.
Just a quick question. On that scale, on the left-hand column, is bits per base, so it's no compression. Does that include bits per base or letters?
Let me show you this. So this compares it to the previous formats. So there's a format change as well as so for us compression is a format change. Hopefully that will come through. But so looking, this is the same scale, but we're going, so we're log again, bits per base. So this is sort of big footprint. That's 0.1 bits per base. That's very small footprint. And at the moment, or before we started, the dominant format, or the dominant two formats, BAM and FastQ that I just showed. So compressed, these are both compressed formats already. So FastQ is compressed using GZIP. BAM is already a binary format. It's compressed to a degree. They're around about the 10 bits per base mark. If we introduce the kind of reference-based compression I was talking about, we can push that back 2 or 3-fold, push that down 2 or 3-fold. If we're operating in a completely lossless mode. But to get any further than that, so that's great. So you get some compression, but to get further than that, you need to do some data loss. And this isn't to do so much with the sequence; it's to do with those numeric values, so they don't fit the reference-based model so well. So we have to do some data reduction and think about that. But in principle, if we do this, we can push really, a long way down. So we're sort of orders of magnitude lower in footprint. But because we're losing information, there are decisions to make. We have to understand exactly what we're losing. And these are just some examples of. So this is where the Sanger Institute is at the moment with its the typical data set that it's producing. So they're the major producer of sequence data that flow directly into the EMBL systems. This is the 1,000 Genomes project, which is a big population variation project in human sequencing. Its releases are now produced in CRAM format and they hit this kind of one. So compared to what they would have been, this is there's already a bit of a saving. So that's useful. So we had a scheme that worked. We had some code that we could demonstrate and we could explore it. But we needed to think about exactly what software we needed, how we would engineer that, and how we would deploy that in a way that's useful to us. And so the first consideration was whether we do this in a local kind of way. So locally, we have a challenge with disk and network. Do we try to solve this locally, or do we try to solve this more globally? And quite early on, we concluded that actually we need a global solution, in part because we think we've got something quite useful. In part because the EMBL, our function is to lubricate bioinformatics, and it's our job to try to help these things happen. But I have to admit, in part because if the world speaks in compressed formats at source, then tools will emerge that deal with those compressed formats. The way of thinking will be in compression space, and our job will be much easier. So it actually makes sense very practically for our data submission services and our data repositories that actually the rest of the world uses the same kind of compression schemes as we do. I can't say the second thing is something that we actually, well, I don't think I'm thinking of it particularly actively at the beginning, but certainly looking back, it's something we could have thought about. Given that we decided this was going to be global, we were going to try to persuade other people to do things and change the way people outside were behaving. It became that we introduced an element of marketing, driving people to do things. And so actually we pitched this always as compression. It's about reducing footprint, physical footprint. But actually a lot of what we've done is working around methods of noise reduction. And an alternative marketing strategy could have been to say, right, we're going to make some great new tools that allow you to get more out of your data by doing this really intelligent noise reduction. We didn't do that, but it's a consideration because that would have been persuasive to some people that perhaps were a bit resistant. And so we had to understand the niche. Now, there have been competitions in the compression of sequence data. We're not claiming that the method we have is the most compressive. We're not trying to make it the most compressive, actually. But we have this sort of 3 dimensions, and we need to find a niche within this. And clearly, you could have really high compression that really squeezes your data down, but it takes an awful lot of compute to do that compression, to put things into compressed format or out of compressed format. So actually, you're replacing a data storage network I/O kind of problem with a compute problem. And that's not so, that scales badly as well. So that's not so straightforward. But also there's the accessibility. We decided that we want a format that's compressed that can be used directly. So the format we came up with, crap. You read it. There are APIs. There's a direct interface into it, so you can directly access the compressed data in an intelligent way, a selective way, in compressed format. So you don't have to decompress. But of course, that means you're limited in exactly how you do your compression. It constrains you a bit, so you're not as effective. So we occupy a space somewhere in here. We're not trying to be the lowest footprint. We're trying to have some high level of accessibility. We're trying to reduce the cost so it doesn't make it too complicated to do the compression or to do this. But certainly, because it's global, it's a community activity. Part of this is us tightening down formats to make sure that we can get compression that is effective and works. But part of this is allowing, setting up the right framework that people on the outside can input how this is used. And that's particularly important when we think about lossiness and how to do which models we use for data reduction. We don't want to be, as the developers of the technology, we don't want to be making decisions about how the community decides on which data should be produced and which data shouldn't. And so we came up with a design. It's open, it's an open source project, open to the community. We indeed focus on direct computational access to the data, so you don't need to decompress files before you use them, just operate on them directly. And we spent a great deal of time working on the various various libraries that people use to access the BAM format, which is the I say outgoing, it's the non or the less compressed format that pre-existed. And so this is a Java library. This is a C library. These are used by a whole load of tools that stack on top. So lots of the high-level applications are using underneath these tools. And what we've done is written the right modules to allow CRAM data to be readable and writable. So you really just put in a flag or say, I want to write or read CRAM rather than so to try to make it integrated with the tools. And then so CRAM is an accepted format for the Global Alliance, which is a big human genomics data sharing, technical data sharing exercise. So we're trying to connect to the right initiatives and the right uptake places. We've had to do extra things because the reference is so important. We needed a registry of references. It's like a decryption key. If you have a CRAM file you don't know what the reference is, then you can't use it. So we have to be absolutely robust about this. And that's a big database that's very fast and responsive. We're still working on this, but we've begun programs of training and helping people to use it and so on. And then we have some principles of development that relate to stability and cycles and so on, testing and consistency. I think that's quite an important part of the engineering work. So we need to deal with lossiness, and we need to think about lossiness, and I won't go into huge detail. I'm illustrating this. This is a model for doing data reduction. I'm illustrating this with two stills from a video series, and actually it's great because demonstrating compression using pictures it's really neat. But actually we borrow a little bit of the thinking from the video as well. So simple models of compression will take, so this is mainly around that numeric scale, the quality scale. So simple models would just say, well, let's quantize that scale. It starts off as a 40-point scale, let's just reduce that to 8.4. So you're just taking, just evenly reducing precision across the whole of the data set. That's great, it can get you so far, but you blur the informative part of the signal as much as you blur the uninformative part. So what we really want are models that are more intelligent, that apply compression differently to different parts of the data set. And so although the data points within the data set are evenly distributed within that data set, so a FASTQ file has data points all in one file, that's what it is, the information is unevenly distributed through that file. So the information content is not necessarily as even spread as the data content. If we have models that are informed by the interpretations, informed by the biology, in genomics we can do this to an extent, then you know which areas you need to focus on, you know which areas are less likely to be important. Developing these models is not finished, it's not straightforward. But the principle is that you understand something about the meaning behind a data set, and you use that to inform where you should loosen precision at the expense of other areas where you should keep precision. And so these two, so this is just, you can see it's just two people walking past each other in a corridor, and these are two stills. This one has no compression, this one has compression, and this model quite simply says, well, where you have movement, that's where the eye will be drawn. So the informative part of this data set is the area where the pixels are moving from frame to frame very quickly, or they're changing very quickly. The rest of it where it doesn't change, well, that's unlikely to be particularly interesting. So what's happened is the algorithm has blurred, reduced precision in the surrounding area, which is the corridor, but it's kept full precision around the two characters where the movement is. And so that's a common technique in video compression. But essentially, it illustrates that you have an understanding of what the most important thing is, and you focus your precision on that, and you lose elsewhere. And this can be quite powerful. So, in terms of getting people to, if we have these models, or to develop these models and to understand how to use them, we published another paper that was, the aim was to get people talking and thinking about this. And we came up with a model for applying this where the community would have an opinion about the different data sets, how much compression you can do. So essentially with the Crown method, you have this model control. You can turn your compression up, you lose precision, but you get a very low footprint. That may be appropriate for some data sets, or you can turn it right down to a very low level, so you have almost no compression, so you keep a lot of precision. And so a lot of this, in economic terms relates to the cost of, so there's a lot of, in the sequencing world, there's a lot of talk about saying, oh, don't store the output of your sequencing machine, because you can just recreate the sequence data. It's just so cheap to run, and it's true that per base, the cost is tending to zero. But that assumes that you can just run your sequencing machine on your sample. And the problem in the genomics world, and it's probably true in the metabolomics world as well, is that actually generating a sample, processing a sample, is a costly step. It involves people, and fuel, and manual intervention often. That's actually, if you consider that in the cost, it's actually quite pricey. So it's not viable necessarily to reproduce to reproduce a data set at will. If you stored some of the sample, you can do it. You have enough to resequence. But if you haven't stored it, you have to go back to the environment, back to the patient. Can you recreate the whole of the study? So based on the model, our model proposes that based on the cost of reproducing a data set from however far back you have to go, which might be setting up a 10-year environmental survey, or it might be setting up a clinical trial of some sort. Consider the total cost of recreation such that if you did something to that data set that was so reductive, so lossy, that you needed to go back to recreate the data set, what would that cost be? And then based on that, you come up with a factor, compression factor. And so where it's very expensive, where you have to run the whole of the trial again, you have to get all the patients to sign the consent forms, you have to go and get the samples. Well, let's not do any loss of compression there. We need everything because it's going to be impossible, very difficult, very expensive to go back and do it again. Where you have something, well, you have to go back a long way, but there is a bank. It's in some place you have to pay to get a cell line, but you could redo the isolation and do the experiment. Then maybe that's twofold. This is fairly routine. Actually, you've got something in the freezer in the lab next door. You can just go and get it, do some extraction, run it again if you want to. And this is something, well, we knew all about this sample anyway. Everyone's sequencing it. It's completely stable. Everyone has this stock. Here we can really ramp up the compression because if we had to recreate it with more precision, we could do it. And so, I guess the focus here is to try to get the community who deal with data, who deal with sequence data, to think about which areas and which applications fit and which types of sample fit these different categories, so we can apply compression differentially. Just a comment, and this came up in the discussion yesterday. So what we're looking at, FastQ, that's not exactly what comes off the machine. In the Illumina platform, there's an image. The image then gets areas get intensities. So you get peaks, and then you you make some approximations, so you end up with a signal trace. Then you remove some noise from that trace, and eventually you get into the sequence, the base called the quality domain. But actually, there's a lot of machine data that's upstream. When we first started out with the Illumina platform, there were people that said, we should store the images. We want to get back to those. We don't believe that the way you call the basis is right yet. But actually, over time, as a platform matures, and we've seen this for other platforms, what starts off as being called raw actually it changes, and so there's a sort of window. And so with the Illumina platform in sequencing, we're around about here, or maybe here. But actually, there's a lot of this isn't raw data. This is something expressed, and in time, things will move further forward actually. And so we're talking about quality scores now, but perhaps in 10 years' time, quality scores, because everyone will be completely comfortable with the method for understanding those, and that will no longer be contentious. And in fact, what happened a couple of years ago is that one of our basic compression models that we apply in CRAM, which is this quantizing of the quality scale, Illumina decided, based on some of the work they were doing, based on some of the public work, they decided that actually their default output was going to be not a 40-point scale, it's going to be an 8-point scale. So at that point, now they're the dominant, quite a single method, they dominate the market. They decided they were going to do this data reduction, and immediately the vast majority of people just adapted to that. A few sequencing centers said, no, we're going to make sure we get the old, we choose to go back to the old system. But a lot of people just flip with it. So actually, what we were considering to be compression and data reduction was no longer data reduction. It was now lossless because people were producing data that was already produced. So so these things change over time, and it's about the confidence of the consumer. It's about the maturity of the methods and the heterogeneity, understanding the challenge of interpreting the data correctly. So just to finish off, so I think we've had an impact. One thing, and this is probably to do with the way we wanted to do this as a global community project. This takes a lot of time. We've been doing this for quite a few years now. We've seen an impact, but there's a lot of, in a way, we're only at the beginning. So it's been taken up, in particular, when the Sanger adopted this for their intern, so a year ago, or so, or a year and a bit ago. They adopted it as their internal working format, which meant that all their data solutions, their data transfers would be in the CRAM format. That was a milestone, and immediately, because they're the major provider of data that goes directly into EBI, that had a big impact. Illumina, the manufacturer, I think the dream is that Illumina will adopt this. They support it to some extent. I don't think you can, the current analysis software, you can't quite want to directly or natively. So they're promising to do it, but they need to see the customers asking for it. So that's the real thing. In terms of our repository, well, it's difficult to measure, but we know we've unclogged bits of network. We have this rapid access, some high cost scratch storage for doing processing of data sets. It needs to be fast because we need to move things around quickly, but we've cleared a lot of that and we've reduced the cost there. Easier to measure is what we actually end up in the final archiving disk storage. So since we've been running, we've reduced what we would have had by 20% and 3 terabytes. That's actually over twice that, because that's just a single copy, it's not counting the replicated data in the remote data centers. And but over time, this will grow and become more significant. So we're now, without doing anything more, actually, it's not necessarily percentage, but it's certainly growing. So there'll be significant financial savings there in terms of buying disk. But another advantage is that because CRAM is a format in which we really describe the essence of data, so we're trying to represent the information content in the most effective way. It means that it's a very strict format, and it has very firm requirements. For example, about referencing a reference, so you have to point to a reference exactly in a very unambiguous way, which doesn't happen with the other formats. So being tight about the format and building compression has given us a data structure that is actually very robust and very resilient. So we've been able to build all sorts of services to allow people to query data that's stored in the CRAM format based on the reference, because we know that the reference is absolutely validated. The CRAM file wouldn't work if the reference wasn't the reference they were pointing to. So we've been able to build services just because we've tightened up the format. And that's sort of aside from the fact that it's a complex format. So finally, the key people, we have one developer at EBI, name's Zaludin, who works on CRAM at the moment, and we have another person over in Sanger who spends a lot of his time. This is James Watfield. He's working on some of the libraries as well that deal with CRAM, and those are really the people. There are a great many people around the world actually contributing, but those are the real drivers of this project. That is it.
What do you do if the reference changes?
It does. It does. You don't need to do anything. So the reference is, in terms of usability, if you want to ask biological questions directly of your data set that are in CRAM format, then the more like your current opinion of the reference, your compression reference is, then the better. But strictly for compression purposes, the reference is just a substrate for organizing reads. So actually the best reference, the best compression comes when you have a specific reference you build for a given read set. So the reference doesn't have to have any biological meaning. If it does have biological meaning, it becomes much more usable. So if I want to say, right, I want all the sequence reads that give me evidence for a particular splice junction, then I might go in and say, right, so I know it's this chromosome, this build of the human genome, this location, give me all the reads. So you can do that. Now, if you're on the wrong reference and the world has moved on and said, no, actually that splice junction isn't there anyway, it's somewhere else, then your coordinate system is you either need to map coordinates or you need to rebuild your CRAM with new alignments. We, as a repository, we don't rebuild with new alignments, but we rely on point people towards external coordinate mapping systems. But your data over time, if your reference changes a lot, then your data, unless you reprocess, your data become less and less biologically directly accessible.
Does the user select specify the reference, or is it like this?
No, the user specifies the reference. The starting point for using the CRAM tools in terms of writing to CRAM is that you have aligned data. Yeah. So it doesn't have an alignment component. So you make a decision about the reference. And of course, it makes a big difference.
Very interesting approach. Actually, my question was a bit open up to everyone. In metabolomics, I mean, I could see having, if you, particularly for MS2, MS to the end data, you could have a reference spectrum, and then all spectra of that same metabolite or identification would be clustered to that in a similar technique used. I wondered how possible that would be. I think in proteomics, I think the massive repository do some sort of clustering like this over their repository. I don't know if it's if they use it for compression, but they certainly use it to cluster spectra that look the same together and then make inferences on that.
Their identification templates isn't as black and white with sequences or bases. So we have compounds consisting out of 6 carbons, 12 hydrogens, and 6 oxygens. It's a hexagon. And then there's a whole scale of how exactly you want to annotate an hexagon. While if you look at the fragmentation spectrum, it would be, all of them would be very similar. But then it's not that one spectrum in one particular compound, it can still be a class of compounds. So it's from that point of view, it's very different.
But if there wasn't any, like say, the reference doesn't need to have biological support, it's to be significant. So if you were just clustering spectra, large amounts of spectra together, and then for all the ones that were kind of quite similar, you could then just store the deltas and do the same thing.
I suppose the question is what no two spectra can be absolutely identical. So how much of a difference is enough to make it significant?
To make it worthwhile doing it.
And is a machine difference or a concentration difference, or is it?
But you could, I mean, but say you can have a mathematical function that defines a spectrum in some way that approximates to what you see, and then you encode your differences to the thing produced by that function. And that function can be produced by doing your summing of what you see a lot of times, or it can be produced in some other way. So we tried a similar thing with the numeric series, the quality scores in sequence space, because there you tend to get, so it's not, I mean, it doesn't look like spectators, but you tend to get a tailing off towards the end of the sequence, and there's a certain profile where it stays high and drops. And so we figured, yeah, there's a mathematical function that describes that. Well, certainly there are known relationships between adjacent data points of whatever order that you could try, you could simplify and approximate. But actually, we found that because there's variation that appears stochastic, we found it wasn't very compressible in our case. But which pushed us towards data reduction more in our case. But in principle, the reference-based modeling doesn't have to be for a dictionary-based data set. It can be for numeric data. And in fact, it's used in video compression, where you have a frame, and the next frame often, if you're compressing the next frame, may actually only tell you about the differences to the previous frame, and the next one may tell you about differences, and then there may be a refresher everything because there's a little bit of extra bandwidth, it's tuning itself, or there's significant change that you want to refresh everything. And those data sets are, those data sets are numeric data sets, where you have intensity, and you have a color scale, and you have intensity, and you have the XY. So, reference-based models can work, but they work better when you have an easily describable reference that doesn't change too often, against which you have a limited pattern of variation.
Regarding this thing, and for example, algorithms like the one you showed today with code data as coefficients on these points. So I think one of the good things about different ways of representing the data, not talking about compression now, is that you can end up with maybe better or at least different similarity measures, which will probably guide better database search faster and maybe, I don't know to what extent. Because usually what you do is the distance or something like that, the distance. Those are most of the basic that measures, and sometimes they're quite efficient.
You need something, I mean, it's one thing, compression within a data set, but if you can compress across a repository, there's possibly significant savings there, but exactly as you say, you need to have some metric of similarity if you want to do this via a reference or a clustering-based system.
So, what you explained, we are doing it right for 2 or 3 years. We have a system that works quite well, and it can be used to try to solve things that are similar. I don't think it can be used for compression purposes, because when you try to cluster everything against everything, you need to make assumptions about, for instance, the number of peaks that you want to take. You can do it, I don't know, most intense, or you can just do it intervals of 100 times. At the moment, there is no, I don't think, computational way to. We are the last build that we made. We clustered almost 80 million spectra. We are using Hadoop technology, and even so, it takes quite some time, and you need to take assumptions in the game, like these things. The distance, similarity distance, you want to take into account, the number of peaks that you want to take into account. So it can be used, it can be very useful, but I think that for compression, I mean, at least lossless compression, but you could use it for that you will lose information.
Well, what about metadata compression? Because if you've got everything, let's say, in XML format in your repository, then there's going to be a vast amount of that metadata that's going to be the same or remarkably similar across all of the data.
What proportion of the storage is devoted to
No. It depends.
Seems very
In XML. which proportion of data, which proportion of MCMLs divided in metadata?
Metadata to actual.
It's very dependent on the number of
Depends
steps.
yeah.
Not
For SRM data, there's a lot of metadata.
what are you trying to cluster the entire data set? So that subset of similarity groups of
we try to cluster
individual
across
spectrum
data
within
sets.
data sets.
Sorry?
You don't need to cluster data. Sorry, maybe I didn't misunderstood. You can cluster the spectrum within the data set.
Yeah, that's what we do.
Across the whole repository.
In metabolomics, it's quite a normal approach to have a reference for sample or a full sample. Use that as a reference, and then look at how different all the other spectra are from your tool.
I suppose I wonder whether, even in a large epidemiological study, you expect significant differences in every sample. Very much in quite a few, almost across the entire spectrum. So, I don't know, I would imagine that there's almost no things that aren't different in a significant way from the group. So that then would afford any compression.
Yeah. And it boils down to the fact that it just comes back to the same question: what's noise and what's not noise, and the noise can't be compressed. So,
But the noise isn't informative though. So if you can find,
but we have the problem that we don't know what is noise.
no, I know. But so it's only this. I don't know.
It's the cutoff.
Yeah, so in genomics, a lot of the application is about finding SNPs, finding variants, and we're very good at finding variants where we're very confident. So we have methods that are tuned for finding variation that is not noise, it's not some error in the sequencing machine. It's genuinely a variation that we want to investigate and make some biological impact. We're very good at that, and we're also, by extension, we're very good at saying, and these are the things that are variants, but we're not so confident about. But what we're not good at, because it's a different kind of job of work, is saying what are those things that are variants that are definitely noise. So it's not very exciting. So people don't spend so much time, certainly in genomics, trying to find variants that aren't variants. And so those things that aren't variants is not the inverse of things that are variants. It's something slightly different. And so we've never really spent much time on this, but actually, if you can confidently call, only a small percent or only a small part of your noise, it may, depending on the data, may have a significant impact on compression.
Actually, thinking about what you're saying, the levels of metabolites are continuous and probably couldn't compress very much the differences between levels in metabolites and reference. But of course, the mass differences on the mass scale should be reproducible. I mean, you've got glucose, which is the same mass, but we can add up so you imagine in the mass dimension, essentially a human metabolome set of masses that correspond to that, and in some way, okay, we don't know the full metabolome, but there would at least be a set of masses which would be observed in most experiments.
As a subset cluster.
Yeah. So that data should be kind of, you should be able to find a reference to that. That there shouldn't be many. Suddenly, if you go
I have one last
yeah,
question.
but you don't need to know, for a certain mass.
The time frame that you showed us that people accepted, going from wanting raw to be stored to now accepting that now this format is good enough. What is the time frame of the community getting to demanding even images now to accepting that?
In this case, it's about, I don't know, eight years or so, where although 8 years ago there were people asking for images, but most people weren't. But there were still a few voices. I mean, at EBI we developed another image-based corner, so there was work going on. But I'd say, I don't know, it might have changed had there been another platform that was genuinely competing very well. Maybe that would change the dynamics. But I think that once, I don't know, so going from fast Q, so bases and qualities, full scale qualities, going down to 8, that took about, when the technology was really mainstream and being used by more than a few sort of specialists, that was 3 or 4 or 5 years or so. Recently, we've been talking about going from 8 down to 2, or down to 1, so 1 is effectively no quality. That's happening quicker, so I think it's possibly moving down, we're getting faster as we go down that arrow. That might be the case. While we've been doing crowd compression, there have been other more drastic approaches that say, well, let's get rid of read identity entirely, and let's just say, just represent the coverage in bases that we've read against different points of reference. Have some confidence on those. So you can't, so it's lossy to the extent that you can't even reconstruct original reads. We didn't go that far. So there is a format for that. There has been a format for some time, but maybe that's a sort of branch of the community that went that way, for particular purposes. But I don't know. I think that without, so if we didn't have CRAM, you wouldn't be able to make these. So the existing format, the previous formats, didn't support some of the compression we're doing, some of the representations very well. So CRAM allows you, because of that volume control, it allows you to set an intermediate to say, well, we're not actually ready to go to a full degradation of quality scores. We want to go halfway, and CRAM allows you to do that. The other formats don't really do that. You either have everything or you have nothing. So in a way, we've sort of maybe lubricated that arrow a bit. But it's a scale of years. And now we have other, we have 3rd generation sequencing platforms that we're working with to do compressions. And who knows what's going to happen. But I'm sure that if you have a number of aggressive vendors in the market, the dynamics will be different to a single dominant vendor who was aggressive, but still is aggressive, but they didn't fundamentally change anything. And I don't know whether things were gradual rather than drastic, though it was very quick. And I wonder if having a competitor and needing an additional edge, maybe that would change things. But I mean, the vendors have a lot of power. If they change something, it's difficult not to go with it as a consumer. But they're responsive to the consumers because the consumers are the ones that their enterprise will fail if people don't buy the machines in it. So I'd like to think it's speeding up, but I'm not sure. But certainly a scale of years, and it's because, in part, it's because it takes a long time to get people to change all of the tools and all of the people have a lot of work to do as a result of this, and that takes time.
So, isn't that the companies are much more open on those platforms? See, for example, that we must this trust the companies and say that we accept sending more data or like a different stages you go through to show you need to build up trust somehow. So if there is a kind of black box that you know what's going on, then how do you know that you can send more data or more data?
Yeah, I don't know if the sequencing vendors are particularly open. You can't just get it. You can't. You certainly. If I want to install the Illumina software as an outsider, I wouldn't just be able to do it unless I bought the license to do that. Lots of the methods are from outside Illumina, and I think they're not fundamentally that interested in the software. They're more interested in the hardware, but obviously need software to work. They have an app development environment on their cloud system, but they.
Just interested how you trust.
Yeah, but I think trust. I think maybe a lot of that takes time to come because you just need to build up the data sets, and people need to see the published studies, and people need to go through years of criticism of that. But eventually, the black box is okay because it's everyone else has done it. maybe that's not right, but it quite likely happens. And people, so something's established is challenged less than something that's not yet established. So sequencing had been with us, so Illumina sequencing had been with us for 20 years. Would a new scientist setting up a study be as questioning of the method as somebody who's looking at new technology? I'm not sure, but yeah, but the trust thing is it's really critical because people, you know, unless the output of something is trusted, then it can be great, but you know, people won't use it. And that's what in our approach, people using it matters most. That's the most important thing.
So I'm going to show a bit what I think, or the way I think that HDF5 can be a very good format, serving even as a base for some standard formats, and how you actually can use this to, in our case, compress and reduce the data size that we have in metabolomics. So usually we've been talking about these problems. We have data sets that can be very large. Usually MR is what you consider a small data set, and we have high resolution MS. If you get even more if it's chromatography, and it goes even more if it's mass spectrometry imaging. So two of the solutions to these problems are usually talking about data reduction methods, and how much can you reduce. It's a very platform specific and the algorithms that you're going to do. But you've got data compression, especially when you're talking the lossless part, which is kind of transversal. At whatever level you have the data, you can apply data compression, and that in theory should help. So my question, or what I'm trying to convince a bit to show, is that HDF5 can be really helpful, a really helpful format to achieve good storage of data with a lot of other nice characteristics and regarding compression. So introduction, and I think I'll say, if someone, I'll try to just show a bit of what the HDF5 is and explain really simply what the characteristics of it are. So I think this is the beginning. If someone has questions after me, they can interrupt. Say. So it stands for hierarchical data format, and I'll explain the hierarchical later. So it's been done by the HDF group. Like you said before, it's been developed. There's a lot of investment on NASA and other big organizations of computing. And the idea is to create with a versatile, efficient input-output container for large data sets or for very big data sizes. And also with a lot of possibility to annotate these data sets and to have metadata on it. So it's a very flexible container. And some of the attractive things is that it's available in most programming languages, and I think it's having an amazing traction in most data science languages. So for example, a lot of people using this in finance, not just omics, I'll say in general. And it's being used more and more. And one of the really good things I'll say about this, of course, it's free and open source, but before that, the point I had there is that, so this has been developed by people who have very big needs in terms of computing, and there was a lot of thought put into a lot of issues that we arrive when dealing with data, or especially with large volumes. They can have some solutions regarding the way we do the file handling and EO operations. And so there's a lot of community effort to actually, from the computer science and software engineering side, to tackle these problems. So there's a lot of thought put into this, and there's a lot of solutions that are already built in. So when you use it now, you kind of get a format that's very flexible and tweakable, and you just have to worry how to model your data in that format. You don't really need to do with software implementations that much. So I think it makes it really, really nice for anyone that wants to come along and use it, because it will mask a lot of the gritty details from us. So the structure now, as I say, why it's hierarchical. So usually you can say, at a very general level, it's like having a file system within a file. So you have the structure with these groups, which are represented in these rectangles. So these things will have names, will have paths inside the file, like Unix POSIX style paths. So if you open one of these files, you can say, oh, I want to go to NMR data, for example, in the diagram. And you transverse this just like a folder. So these are just subfolders within the file. Then inside you have data sets, which they can be of multiple data types, but usually what they are basically coordinate-based arrays. So the same way that you store arrays in MATLAB or many other languages with, and you access them with coordinates and slicing notation, you have these in dataset. You have these are the data sets in HDF5. For example, we put a big binary file there, and then you can slice and dice and read it from the file directly. And the other thing is the chunking, and this part is very important. So the data set can be further subdivided into chunks, and then actually it is going to be very important to understand compression, because the way the file is done, so the access to the data from the data sets will happen to each individual chunk. So I can have a regular read of on a data set, and I can actually chunk it in smaller spaces. So I can define bigger chunks, smaller chunks, so there'll be contiguous blocks of data. And every time I read the file, if I select chunks like the ones I've exemplified there, if I want to read the whole block, I'll have to go and read all of these individual files. If I want to, if usually my access to the data means that I want to take the whole data set at once, I will define a larger chunk because I don't have to make so many calls to the data. So this is the chunking is flexible, but it's one of the good things about HDF5 because you can tweak it to different access patterns. So by defining the chunk size, you'll be playing with how fast or how efficient you can be in the access to your data.
That chunking is predefined when you decide how your data is going to be stored.
Yes, I can define, and the tools you can actually open a file. I think it's actually important. You can open a file, and if you don't like, if you think you're reading it too slow, you can actually repack it. But it just we just did some stuff that with a simple command. You just change the chunk size or change the compression. The other thing is the compression works at the level of chunks. So each chunk will be individually compressed. That's how it's going to be. So there are other things. So there are attributes that you use to store metadata. There are data spaces. There's a couple of others. But I'll say let's focus on these three because that's how we can understand how we can play with these to get good access, good compression. So it's a B-tree structure. As you said, you can put strings inside. There's other types of data sets. So the idea, of course, when you have such a flexible format, I would say you can start thinking of it in a different way because this is considered to use in big data sets as well, mostly. So usually we think of standard as one per file, but when we have data that's regular across assays, because we can actually think, well, instead of just putting one spectrum on one LCMS assay on one of these files, I can actually put more. And then, so for example, if you go to the Metabolites, we end up downloading a lot of zip files with individual files. So why not just have a single HDF file with all the data inside that compressed or not, and with the metadata or other things as well. So it's just a matter, because it's very flexible, we can think in different ways we can organize the data. So regarding compression, so there's another thing in HDF5 which is called the filters. So the filters is pretty much, the way that compression is being done is you apply these. So when you download HDF5, you already come with tools, gzip, zlib, compression, and LCF by default. So it means that everyone that downloads or gets your file from whatever, from a database repository, the moment they have HDF5, they will be able to read this. They will be able to open the file as they want. So depending on the chunk size, depending on the compression you're placing, the user doesn't have to care about reading something, parsing something. They open, it is there. It's completely transparent to the user. And the other thing, as I said, is that regarding we're going to have the reason why we have different compression filters or compression algorithms built in is that the idea of this file is to be not just necessarily for maximum compression, but to allow trade-offs between compression and random access to the file. So we have filters that are really good at making very compressed data, and we have others in which the point is I'm not going to have such a big compression rate, but I'll be able to have very fast deflation and compression, or maybe using parallel access to the file. There's a lot of different flavors depending on the need. So if you want to use another visualization tool, maybe you just don't want to go all the way and apply the strongest compression algorithm. You can go for some of the other ones that are a bit more, that trade the compression rate per deflation, or maybe not compress the file at all in this case. So there's some compression algorithms are already provided. Some of them, there's others that if you want, the file has been registered officially, so it's easy to, you can compile specific softwares with it, and they're quite followed, and they're quite, so you're not going to be the only person doing it. They're registered there, there are curators for it sometimes. So the thing is, like I said, each chunk is compressed individually, so are compressed too. So this means when we play with these things, they're going to affect the ratio of compression and the speed. So I did a simple example using a small NMR data set. So the idea is that in NMR we have each spectrum with a single, or we have a data set will have multiple spectra, 1D in this case, not 2D. So the idea is that I picked up a spectrum 2651 on the NMR, and instead of doing one HDF5 for each spectrum, I put them all together, the whole data set in an HDF5 file. So they have 128K points, and so I've adapted some of the things that I use most of the time when using HDF5 with NMR. So I put a group for the data and another one for metadata. On the metadata one, I placed a big string with the spectrum ID. So just, for example, it's just a metadata saying that row is going to have that spectrum ID from the study. I've read the parameters from the vendor directly to the JCAP-DX from Looker, and I've loaded it to a string without compression inside. So that part is not going to be compressed. It can be. And then for the data, what I did is look across the whole files, and they have the same more or less ppm chemical shift windows, but sometimes they're small, slightly different. So what I did is we interpolated to a common one, but respecting the range, so just to make sure that it makes sense to have them all together with the same digitization rate and all that. So I put the original and both the real and the imaginary part, because in NMR the process data we have, but this is not PDF IDs. And then I compared it with the vendor. So when I say with the vendor, it's picking up the P data, process data, and the metadata that we have, and doing it for the whole data set, just taking these files and the respective folders. And then I did a comparison with 7-zip, because it's usually, you achieve better compressions with it than with WinZip, at least in my experience. And then I did some comparisons using HDF5 no compression, the gzip algorithm with a mild compression rate, and with the extreme one, and then the other that comes from default LCF. So there are some differences there with the floating point. I think it's quite an interesting point, is that why usually the data that we have in NMR is integers, is in integer numbers. So by doing the interpolation, I was actually converting them to floats. So to a certain extent, you're increasing the size of your data. This is a slight mistake that I did while addressing, because I kept it here because I was showing you checking with Jake, and apparently a lot of tough data is happening to a lot of tough data. So I think it's quite didactic to keep it there. So the idea was that I was putting this into the structure, comparing, so you get a bit of a reduction from the vendor, but not impressive, using the float. Then the HDF5 you get. Also, you go from 2.9 to 2.05 gigabytes by using mild compression, and then, of course, the compression rate to get a bit of diminishing returns after a while, increasing it. And sometimes you don't really see big differences from going gzip 4 to 9. So I'll have to try this with a lot of data sets, because it depends on the structure of the data. So this might not necessarily be the same in all data sets. And the other thing is to try to keep the original data format. I typecasted it back to round to the nearest integer, and put it back in integer, which was supposed to be the original data type. So again, there's no difference in having float or integer without compression, but it seems that you can get much better compression rates with integer numbers. So you go from 1.2 gigabytes while it was 2.9, and you also don't see that much improvement with gzip 9, but the other LCF is just another algorithm that gives you mild compression but better access. So I just put it as an example because it's a default. So I would say I've been using HDF5 in other contexts. So part of these compression examples that I'm showing now is more like I try to play with it a bit to come and show here, because we are worried more about data reduction and compression. But the reason why I started using HDF5 is more because of the access to the file. So I've been playing a bit with some examples. So I think it links really well with SQL. This kind of a diagram. The HDF5 example that I have there is actually quite elaborate. I don't use things like that anymore. I simplify it. But in theory, you can, in practice, you can have a metadata stored in SQL and use the language, and then keep the selection or the coordinate space where you find everything on file, and have a hybrid SQL HDF5 on your LIMS system that stores the data much better. And you can also develop your code or objects in which you're processing pipelines in ways that you read objects from HDF5 or you read objects from this type of combined queries, and then you either map them on memory or not, or just keep it pointed on the file for other types of algorithms. So the SQL part, I think, can be made in ISATab, like you can make an ISATab reader. Maybe you could do a prototype at some point in which you download something from a database, parse the ISATab to a quick SQL-like HDF5 example. And other things is for the way it happens is that as I've been using HDF5, it's good to define a standard format and stick to it in your code. And this, for example, from some direct infusion, a diagram of what we do. We tend to have we have sometimes we analyze things by plate, so we have internal QCs and all that. So you can store all your data pertaining to a plate on one of these files, keep all the quality control information there, some basic preprocessing. And the other thing is because this enables algorithms out of core, you can have the data on disk and read it as you want. It's actually quite good because you can process big data sets without forcing people to go, oh, go and get more memory, go and get more memory, because sometimes you don't really need it. A lot of operations are done, you're dealing with a subset of the data and you just don't need to load everything on memory. So you can use this as a kind of, have the data on disk and only take and improve the type of I/O operations that you do with your code. So conclusions, I would say, why use HDF5? Well, it handled a lot of these issues for big data handling and compression and all that. So you worry more about modeling your data and setting what do I really want to have stored. The same thing that we did for the XML formats. So you can use the attributes or even don't put it as XML as I'm saying. Or there are multiple flexible options to put the metadata in there. You can have ontologies as well on the attributes and metadata. They can be whatever you want. Compression options, I think it's the same. You can get the same compression as you would have in C or other things. You can optimize the access to the data by playing with chunk sizing and compression. And the other thing is that you tend to not avoid data duplication, because if you have everything in zip, if you have to work with it, you want to save it, and then you kind of do all of these things. While here, you actually go on demand and decompress on demand from something that can be very neatly. Well, as I said, are really interesting extras. Yeah, there's parallel versions, and it's really good to have all the data on this.
One good question anyone has, and then we go to answers because topics are based on that. At the end, we have a long discussion. Okay. If you want to ask your
it was more about, are there any hardware specific drivers or anything more on the eye level that underpins this to speed things up, or is it just any file system underneath you?
Any file system.
So is that the normal application of this? It's not, but are you able to speed up the decompression of a data chunk based on a separation of the structure of the file on different?
The structure of the file, by playing with it, you might be able to get, so this is how you model the data. Better ways to model the data, worse ways, because our data tends to be quite regular. I mean, to some extent, LC, MS is not going to change the data structure from one day to the other. Even as field-wise, we can have recommendations of how we should model it for efficiency. So I would say, for example, even with the chunking, if you have a visualization tool, maybe you would want to use some of these things to repack, or on your part of as part of your pipeline, you would want to maybe take a compression and do all of these things. And this is very, the moment you install it, it works. Okay. It's really not a file system dependent or anything. So that's one of the really good things, that it standardizes a lot of the data representation, data type representation, file access from you. Obviously, if you have solid state drives and HDD, you're going to have differences. Maybe you can play to leverage that. Maybe in some cases you would.
So, but that's just in the normal sense that you could do that anyway. So,
yeah.
Okay.
Yeah. And yeah, that is this one.
Nice. Is there anything? Ticket? Did we? No.
Okay.
Reboot or the plug.
Thanks to the excellent last talk, I don't have to go into too much detail on the HDF5 slides that I've prepared. So mainly this talk is talking about various things that we have done and looked at in the Proteomics Standards Initiative process regarding compression. and also what we're now looking into in terms of HDF5. So you've seen some of these earlier. Vendor data, here's a graph. Vendor data is at 1.0 here, a raw file. I believe this is Orbitrap data set. Great, you centroid it, it's tiny, but you lose everything. Profile mode, MZML is almost more than twice as big. So one way we've been we've been talking about for the last about 2 years or so at the PSI, and it culminated in a paper that came out in MCP last year, was some simple methods for trying to compress the actual MZ intensity data. This is called NumPress. It's 3 or 4 different fairly heuristic algorithms for, and it works on 2 principles: predictive coding and some slight truncation, lossiness, but nothing that has any real effect. We're talking about truncation at the level of 1 ion per data point at very most, and usually even less than that. So this is just showing one spectrum as you get the actual data in MZML. So on the left you have the intensity values, over 100,000, and then on the right you have the MZs. So the first thing that you can see is that the MZs are really inefficiently stored in MZML. And in fact, probably, obviously I don't know, but I suspect most vendors probably don't store the MZ values, they just store the curve, this parametric curve, which is just for this TOF data. Oh no, is this TOF? This might be TOF data, but anyway, it's just the quadratic equation between time of flight and MZ. Fairly simple thing to do is a delta encoding, which is where you just, for each value as you go along, you just store the difference between that one and the previous one. So that makes things very compressible in MZ, because most of the time, once you've done that, you have very small values here in MZ, and in fact, that compresses away almost entirely. Because of the noise situation in the intensities, it doesn't make a whole lot of difference in that if you try and store everything losslessly. But NumPress has a certain algorithm that will store each delta for the intensity in about up to the paper, but I think it's 8 bits or 16 bits, just the delta, which from numerous tests we found that there was the difference between that and the original data is so small it's completely insignificant. So NumPress as it is gives a decent, modest compression. So from 2 point a bit compared to the raw data, it's now just below the actual vendor raw file. And of course, because this is something that works on the continuum data and relies on deltas, there aren't any correlations in deltas in centroided values, so it does nothing at all to centroided data. So what's missing from just using NumPress? Well, NumPress compresses the binary data, but it doesn't compress the metadata. So, for instance, for SRM data, the metadata might actually be rather large compared to the actual content of the chromatographs in that case. The other thing, though, is that we compress the binary data in MZML, but then we base 64 encode it to put it into MZML, and base 64 encoding is rather inefficient by itself. So actually, if you then gzip that again, you get further performance, further improvement. The trouble is, if you gzip the whole MZML file, you've lost your ability to random access it, to access each spectrum using the index. So there's one way that has been used before for genomics, and this is called blocked zip format. It's a fairly simple extension to gzip because there's a little header in gzip, and actually you can concatenate gzip blocks, and any old gzip program will unzip a bunch of concatenated zipped blocks together. So if we can actually just gzip each spectrum separately and stick them all together, then put a little binary index on the beginning or wherever that we can interpret, then we can actually just unzip that part of the MZML and read that, and we still have random access while gaining the extra compression. And one good thing about this is that it's backwards compatible. You don't need to use a blocked gzip unzip program. You can use any unzip program, as I said, but if you do use any unzip program, you go back to not being able to random access read it. So at the latest PSI meeting in Seattle, we were in discussion about Eric Deutsch there had someone working on that, but they're not working for him anymore. So it stalled a bit, and we kind of taken up the slack there. But we are going to compare it to what we propose, which is HDF5 based format. There has been HDF5 based format before. Here's MZ5 from the esteemed group in Harvard. This, obviously I don't need to talk about this. The slides there if anybody wants to read it online. Firstly, MZ5 does have predictive coding in it. A very not that numpress is particularly complicated, but MZ5 does have this delta encoding in for the MZ values. So actually, if you see that you do get some compression with MZ5, quite a lot of that is just because they delta encoded the MZ values, which isn't in the original MZML spec. The other thing that MZ5 does, or rather HDF5 does, is that you can store the floating point data, because it's all floating point data. It's essentially stored in MZML, even if it's integer data underneath. HDF5 can store it in a better compressible way. So here's a bunch of 32-bit floats here. Let's see, this is 5, and here's the values here on the left of these 5. So MZML will just store them each one after the other. And when it's doing the compression, because these are small values here, or these 4 here are integers, you see that you see that 1, 2, 3, this is the same as 1, 2, 3 as this. But because they're in this order, it can only squeeze those 3 into some code, and those 3 into the same code, and those 3 into the same code. It's not all that efficient. It's a little bit compression. But imagine if you, if instead of storing it that way, you stored all the bytes, the top bytes first, and then you stored all the second bytes of each floating point, and then all the thirds and all the fourths. Then what you get is here's one that's compressible because it's all pretty much in the same order. And then if you have a bunch of those that are all integers, like TOF data, all of this second half gets compressed down to basically nothing, because it's just a whole huge bunch of zeros. So that's something that's just for free in HDF5, but is not in MZML. It could be put in MZML quite easily, but NumPress does that pretty much in any case. So MZ5. This is a little viewer that will view any HDF5 file, and what the MZ5 guys did was they mapped each node, each element in MZML to a data set here in MZ5, and they mapped it rather like a database schema. So it's actually all hard coded in ProteoWizard of what makes up each table. And you have one table for your spectrum data, one table for your binary data, your CV params here come in a table, and then a table full of the actual descriptions of the CV params. But it's quite difficult to actually look through this because it's really been mapped here like a database schema, like if you have a particular scan, so a particular spectrum here, it's saying that you have CV params from 67 to 77, so you've got to look in this table. Here are those. You've got your values here, the actual, you've got your what the CV param is as another foreign key, and here you've got your ID, the units I mean as another foreign key, and you've got to grab those out and look in another table, and then finally you get that. So it's not particularly easy to look through. It's certainly not like XML. And it has some problems because at some point they decided probably it's too many tables to have another table of scans, another table of precursors and of products. So they started using these HDF5 variable length fields, but unfortunately the Java library doesn't support these fields. So it can't represent compound structures, so it has to access each individually, which grinds things down horribly. The writer can't write these at all, so you can read them slowly, but you can't write them at all. But it gets some decent level of performance. This is MZ5. Not as good as NumPress. You could have NumPress inside MZ5, but I don't think ProteoWizard supports that combination. I'm not sure. So our approach to make things a little bit easier, but still take advantage of everything that HDF5 has to offer. Firstly, bring your attention. I mentioned it earlier that NetCDF4 is actually using HDF5 under the hood, but it simplifies it even further. So there's the API for accessing and reading and writing NetCDF4 is rather easy. There's lots of tools available. It has a pure Java library available. So HDF5, I believe the Java you have to use the C bindings underneath the hood, but they've actually got a pure Java library for the NetCDF4. And the other great thing is that you can read and write data sets directly across HTTP. So our suggestion is quite simple. It's keeping everything that's been done in the XML with MZML, but actually storing it within a HDF5 container. So it's a hybrid approach where we have the HDF5, we have on one side we have the XML, but we don't store any base 64 encoded binary data. We take that out and we store that as a native HDF5 data set. And both the XML and the binary have index data sets, so you can quickly go and get the metadata for a spectrum, or the metadata for a spectrum, or the binary data for the spectrum. So as was said in the talk before, you get all the benefits of HDF5, which you wouldn't get if you were just a simple block gzip approach. So pretty much finally then, here is the final results we got with that data set. So because of the even when compressed, there's still a little bit of extra overhead with the XML rather than the database schema that MZ5 created to get as much compression as possible. There's a slight overhead here with our approach. When you add numpress into it as well, it gets a lot less. So now we're actually at about 70–80% of the vendor format data. And finally, I had a talk this morning about it. I just put this slide here in case anyone online wants to have a look. That's going to further, and it's as was discussed in the first talk today about compression and noise reduction is basically the same thing. So our noise reduction algorithms are quite good at compressing too, as long as you believe that we have kept everything that you're interested in. So that's the acknowledgements.
Any question with the first speaker? Short question, then great. Come back in 15, 30. So any questions with the first speaker?
Do you think if the community decided to go for HDF5 adoption for representation of large data of whole studies, it might be a problem?
The whole studies?
Yeah, that was kind of like Then would we need to have some discussions on the actual structure? This probably goes to both of you, or is it kind of obvious?
It's very obvious because there's a hierarchy of folders that you have in HDF5, and it could just be one data set. But then, of course, your system is putting them in the same data set.
Yeah, it depends on which phase it is in. For that, the example I did was putting them on the same data set. So I guess for a study, or to keep it compressed or something like leaving a single HDF5 if you want, that could be a solution. And we could actually split them in different data sets as well. I wouldn't have gone into that way with the LCMS data. Maybe
Which way?
Just putting all of that in.
I see. Yeah.
So I think because we tend to have, like I was saying, the data structures that we use that represent our data, they don't change that much. I mean, I'll see it's 2D, it's going to be a few years. It's not 3D. That's maybe with the iron mobility. And so what we will have are different access patterns. But I think we can. It's once a lot of people, the initial process to start this development software using HDF5 will need to come up with a merge tool. What's the most efficient way to store a data set of 2D, 2D data like LCMS or whatnot. And then those will be fairly. Sorry.
One thing I was going to ask about the CDF5 approach there, where you bring more than one spectrum into a single HDF5 file. It's because you're not really aligning much with the use the ability to do sort of variable-wise slicing through multiple spectrum.
What do you mean with slicing in which dimension? Because
so
what we can
say
do
Y
is
and Z.
you can't do that in MZML.
No,
but if you read in, or if you and it's the same with our CMAS approach, because that converts into a regular grid as well. You could do that. But yeah, if you're just storing the original data in the original way it's being collected, then you're going to be limited, that you're only going to be able to index it by spectrum. I suppose that's where David Boussy's approach with the MCDB comes in, because they can, I can give you the link to that. They can, because they chop up the raw data into rectangles, they do index by MC and potential, and they use that in their new software package to allow them to extract XICs.
So from a user point of view, it's almost access the data, they're not familiar with its format, then it's a GPU, a better choice, because not a better choice, but more intuitive for them, because they can understand. Because if they
it's still MCU intensity pairs. It just allows them to grab out essentially a strip they want, a strip in MZ, a strip in potential time strip. So yeah, it is a bit more intuitive, and it's probably better for application as a backend to the software package. But they can't compress that data anywhere near as well.
But with the same density of 4 or the other ones that you suggested, that is HDF5, would it be equally in a way to
you could
say
yeah.
analysis, a single
Come to think of it, of course they use SQLite, but you could use their way of organizing the data in HDF5, and you might get the best of both.
So it goes by how you structure it, right?
It's my point to specifically to allow what Jay was saying, to slice across variables. So for example, we can do profit applications in terms of NMR. And now it's interesting to have the data in a way that you actually from all data sets, or maybe for parallel applications like that, to actually take the slices or the regions of the spectrum that you're interested in. So it would be required to take the spectrum points. The other thing is maybe for 2D NMR, for example, it's also another area where it's actually might be really interesting if you can slice across different spectrum within areas as well. Because like I said, put it as a 2D example, it can be a 3D. And the syntax how you handle these things on the software is the same way that you had arrays in MATLAB and with the index implementations. So it's more, it goes down to the access that you would like to have.
If you want to have that data access, the question is whether rebinning, resampling is acceptable to do to data.
Yeah, it's a short break. We can be in like 2 minutes. Yeah, 20 minutes.
Yeah. So what is the
Good question. Yeah. We just actually press file to 0.5. That's apparently not hearing at all. That's why we save the next one. What I did was
I would be here after you.
We did a firing package. It depends on five. And when I did my DSO effect field,
I can write
that adds the line because I opened the fucking and now this floats in 135.000 reads.
At least.
It makes a little because it's overexciting stuff. We just got 0.5 megabytes. No, it is. Yeah, it's not hard.
Maintain the standard. So it's no point in
But that's fine. Yeah. So we actually so what? How much is the service?
It's zero, it's lost. To make it force the bypassing, so it's still afloat. So the whites will be wiped out. And we're losing 0 and 0.5 megabytes for 4. So because I did it with this module, we actually checked the errors that are not standard. And it says it's scanning it seems that so many people are using these two. That's clearly anyone
so you see a different
a bad deal on data compression. Even using MZ5. But we actually one we have. It's actually more complicated because we use the it is.
So what? So yeah,
and it's just because 4.1 gigabytes to 0.5 without a single compression algorithm, just like data. So MZ5 is not for CMS. I and so I follow a lot of the data sets approach. So I don't have one individual file because even NMR exaggerate by just this lab. And the direct function is also a CMS file. We have the scan so I think to because so the user just install and then it doesn't have to do
but when it
benchmark. They train us a lot of overhead.
So let's say the FDA is an LP. You have to change. Yeah. Okay. So you have to. So you typically
So it's only 50%. And actually, it's not like it's almost a shame that.
Okay, so you have a set of, okay, so the requirements are very close. It's not, you have to speak like that into the presentation. So recording the size of different presentations. But you have it immediately. If you read something, if something changes, then you have the right to say that.
All things that if you understand it, you will keep the control, keep the standard check software. Say this is the standard level control. You can be thorough. You can have validated parts of the tree that you have to solve in the roots. So you can have software that just take part in it. So you can even make the file grow as the analysis goes with different reasons, or if you want to form repository with it. For example, we in a lot of objects,
So yeah,
we can
so that
inside stack trace on what was happened. So if I want to recreate an analysis, now I can keep a very true place data was open. That's 5 to solution over
smaller
that spec was called on my sources. So you can do all the types of publications.
So
pretty much drop that data to see what they want.
They're always routed through.
First, the two options.
Yeah, just to, that's where I'm arriving from.
Right. Yeah, that's different. That's different philosophy to be on coding. Philosophy says easily.
Yeah, I think a lot of algorithms are just trying to do that. You can play with the IO.
So that's not that when you present something, so there is a notion in terms of the scientific record.
The other thing is,
You
we are
something used for someone that's not analysis
you are
disappears.
that much about standards. You are something like
It's not your function.
you think metadata that needs to be described. I was actually saying in the beginning, and some of my formats, I'm saying I'm flexible. If the field wants to define something, I'll not readily. But usually, use my standard SQL. I will see
No.
the data. That's a metadata. Example, I'm working with the epi studies.
But I see there.
I don't when I go study metadata. Yeah. So if I want to send,
if that becomes
if I want to send a database, if I want to send data to someone, to these, one thing is the assay metadata.
It's easy to use that to expose data.
Most of the times, just when you actually use data,
then you have you've introduced this as a tool.
while the other ones you tend to query them extensively. And you want that thing to go fetch whatever you want from the data, especially if you want processing volume and go to further, always together. So you get one here, the other one goes to whatever machine learning statistics you want. Because that's really, I was writing from the other one. I want you to do these things together, and I will have a standard format. Tables from big word study.
Right.
Nobody wanted levels of data. We will share the data, maybe an asset. Everything, even data fusion. This is another part. So it's just because I was writing from a different point. Makes me very fast, efficient, nice and lazy.
But this series is just having flow. Just basically the next
So, and then is there ever a flow from the exchange back into the So, because in a way, if you get something that provides data into the system, there has been a structure in it, there's been nice in the way the system with standards that do this. Could this be a feed into the repositories?
Yeah, well, all the data changes.
It's exactly.
So like, use that if they say, okay, I want to get my web drop down button. Part aggregate, they're only really not those organisms you need
I just think it's interesting. So we have a CISO
Market licenses.
we have brokers who set
Somebody
themselves
else.
up.
So basically,
And sometimes that's software that provides pragmatic solutions. Other times they just write software.
Ridiculous. You can go there
They do something that structures data. Maybe use
Okay.
tons of different messages. Then we have other groups of people who, and this is probably quite established. We build layers of discovery services and visualization services. They don't come to us directly. Yes, they usually use that service for the groups of generating infrastructure. And it's sort of surprising in a way that those people don't actually, they're not usually the same people. So you have brokers inwards, brokers outwards, that they choose. It's rare that they're both, which is a bit surprising. The things you did service projects, maybe not so surprising. But what we don't have is we don't have an aggregator.
That's
that sits on the top and tries to gather data from all different repositories. But in part it's because we already have can exchange. Principally, three core, for example, stacks, use. We principally we might do a regression, but in practice, there's some small combinations that don't quite work. So you have very big projects that we can't transfer the data. No, that's data. So, yes, everything. But increasingly there are other people who have data sources that for different reasons don't become part of the public sector. So we also encourage them. So there are people who particularly trying to data, filling the data. What some level here is exposure. So can't comply with the standards for exchange. We could maybe expose something, yeah. At least to the point that discover data fit in some form yeah, so there's no obvious, there's no instrumentation, there's no function. I mean, there's one of the humans. So I think what we will see is that specifically it's about federating, having federated access to data sources where you can't share the but it's very specific. It's very big use case. It's very specific. There's a generic concept of putting this all together and new discovery services. People do it on one of the nodes. Yeah. So they don't do it on it's not the yeah.
My philosophy is that my system should be able to reach today's lightweight. Yeah. All things on that need to be very so when you just have to provide using provider fees. If you start needing it, you also have an in-house, you have your in-house system. And so a company can download over their own service,
Yeah. So you publish the. So this set of things, set of information you expect. Do you
No.
Changes.
More or less.
right?
But I've never come as far as just staying home to the operation.
Right.
And like I said, this spirit like wait, I have the title, description or summary, submitter, and the link, original data, and option, and every provider. In my system, that's data. You figured it? Yeah.
In your systems.
In my system,
Okay.
because I saw that parties have different
Yeah. Yeah.
So I was like, you need to guys sort it out, then we can give it one level higher and make the things required or you just go and figure out, it doesn't matter.
Yeah.
Yeah.
Yeah. No, it's interesting. It's interesting things that you really would think could be organized into a structure. Just aren't. People who disagree on one detail.
Let's start with first step. There, it's not. This has been there for this I worked for this basically. I really like it because it's web and it's very it's not the bonus.
Yeah, you've got something real.
Yeah. Yeah, indeed.
Yeah, so this is consistent across your core providers.
Indeed. So if I now do this for our library, it shows the exact data structure.
Yeah.
Yes,
That's the thing. The authors may think that.
Yeah. Yeah.
Are you going to be here tomorrow? Okay. It's not because I'm going to leave soon. Yeah, I have for the platform. So I will see you tomorrow, but just in case you want to.
Didn't that work anyway? Stop breaking the table. It's going to be off the wheels. So you had it working in production or something. I think I improved it.
And again, because any
Okay, sorry. Yeah.
Anyone's online? Robert, online? You have your presentation, somebody? Have you uploaded to the? Is it on Thursday or? Just on the presentation. Okay, nice one. Which makes that sense.
And it's roughly what
When you look at by a phone or by a computer? Robert, is it a computer or is it phone you're connected? Yeah, this is wrong. So you. Are you still there? Robert?
Yeah, I'm here. Sorry, what did you ask?
I just wanted to know if you're connected via your computer. Should I make you the presenter or are you using your phone?
Sorry, I hear a background discussion, so I think.
Oh, is that microphone then? So I'm asking you whether you're on your computer connected so I can make you present that, or are you using your phone to make it? Just wondering.
I use Metabolomics.
Okay.
Well, I don't know, maybe a presenter.
Fine.
So no. Can you click there?
So I can make you a presenter. So now you're the presenter. Okay, can you see? Do you see it now? Yeah, now you should be the presenter.
So do you see my slides?
We see your slides, yeah.
PowerPoint just crashed.
Or maybe if we are using ours.
Okay, so do you see my slide?
Yeah, we are seeing your slide because we are still using the desktop, but I would assume.
Okay. So if you see my slide, so it's fine. So can I go on?
Do you want to change the slide so I make sure we are in the right setting?
First slide. Do you see my first slide? The big data metabolomics and so on?
Yes.
Okay.
Hi, Reza. We're on the WebEx and we don't see Robert's slide.
Because that's what I was wondering now.
share this.
Click on the WebEx.
Or you can present my slides and I will tell you next slide, next slide.
Val, do you see the slide now?
Now we see it. Yeah, now we see your desktop.
Okay. Okay. Let's try it. If it didn't change slides, I'll change it manually. Okay, are you ready? When you're ready.
Thank you.
So, hello everybody. I would like to talk today about our perspective, how to deal with really big data. So please, next slide. So, well, we have to ask what we would like to do with our data. So, because that's actually determines the way how we process and store and compress and all other data processing. Actually, we don't want to create a data graveyard, so we don't want to have just a heap of raw files that cannot be accessed. There are no index that cannot be searched, that cannot be calculated and classified, and so on. So we need the data that are fully accessible, that are searchable, and we can do in a real time all the calculation we need for our metabolomics studies. So we need the data ready, and that's the issue. And actually, next slide. The way we deal with these problems are chromatographic libraries. So we actually extract the useful information from the chromatograms and put this chromatogram in our libraries. One of the biggest advantages is you have all the relevant data easily available. So you can search them, you can classify them, you can do with your data whatever you want. This is a data reduced chromatogram. We significantly reduce the amount of data, and these data are put into database, so they are indexed, and we can do whatever we want to do with the data. And the chromatographic does not go back. The chromatographic data are organized in a similar manner like spectral libraries. So you may have a record with a sample as an organism, and you can do any type of phylogenetic tree or organization of your data. You can classify the data if you want. Actually, one record is one chromatogram, and you can have for one study like 100 records, 100 chromatograms, and do whatever you want. Next slide, please. So how do we do this data reduction? We are working with a high resolution data, and we are working with MSN data. So we need to do the data decomposition. So we need to extract the all useful signal which is present in the chromatogram. It's kind of picking up front. So first we extract everything what's there and what is useful, and then we put into database. So it's a little bit different approach like many people in metabolomics are used. So they take the raw data and they do big picking with all the algorithms. So you have to do this approach in advance. So we do component detection. So we detect all reasonable components, and we extract the spectral tree. Of course, those triangles which correspond to one component, the spectral tree of unknown component, we don't know what it is in this stage. But later on, so we can obviously do library searching and annotation and assign proper name, account numbers, and so on, if available. But as you know, in Metabolomics, 80% of those peaks will remain for a long time as unknown. So we still treat them as a statistical object. And this information goes to the library. So please, next slide. So that's our software implementation. As you could recognize, this is quite an old Windows view. This technology is 10 years old, and we have fully functioning software for this type of data. So it's present in the mass frontier software, and you can not only build the chromatographic libraries, you can even edit every component. So in the lower window, you see the component editor. So every component can be edited. So you can assign chemical structure if you know what it is. So you can search it and process all those components. Next slide. So, and this is just another example of a very complex biological sample. So if we are able to do proper component detection, so because obviously we don't want to miss any low abundant compound, because this may be interesting, this may be maybe the most important biomarker we are searching. So therefore we have to be absolutely correct. So you go next, please. So this is the enlarged view of one of a particular retention time window. So based on the component detection algorithms, so we actually extract all the components. I have to admit, so we still need to work with the threshold. So you may say, well, lower the threshold up to the 0, but then obviously the data compression will be not as effective as if you make the intensity threshold higher. So yes, I have to admit there is a trade-off. So between the size of the data and information we don't want to lose. So it's, as I said, it's not always 100%, but this is one way how to do it. So if you go please to the next slide. Okay, next. So this is another, I believe this is a plasma sample. So again, we have around, I believe, 8,000 components. So this is pretty much, I would say this is like 90–95% coverage of what's present in the plasma. You never know in a mass spectrometry from this peak whether this is an artifact or this is a real compound. So there will be always a gray zone. So I cannot guarantee that every triangle is a real component. So, but we all deal with this problem. So when this component detection cannot completely solve it. So if we enlarge it, so you can click another. Okay. So you see this one more. So you see a myriad of components. So this is a data reduced chromatogram, which goes into the database, and those chromatograms can be used for classification or any other studies. The one with the biggest advantage is all the spectra are indexed, so they are searchable. You can compare the spectra. You can actually compare the identities of the peaks. This is the way how we deal with mass frontier data. Actually, we didn't implement it yet. you can put more components in one data file, so you can actually do alignment. That's what we are not doing yet. So we don't do the big alignment. However, as we have a spectra of those components, so based on the spectrum comparison, you can do in the future much better alignments than just based on the one MZ values or based on the headers. So that's pretty much it. This is the way how we deal with big metabolomics, big data metabolomics. Thank you.
So, any questions? So I have a quick question because I was trying to understand. So essentially, for example, the current slide, you're not setting up any threshold of where is the peak and where is the baseline. Just trying to essentially take any profile that is potentially a peak. Is that right?
We do, when you are doing component detection, you may or may not set a threshold. Because you may have a very small spikes and there is definitely a lot of noise in those data. And therefore, as I said, this is a trade-off. So usually we do set, actually I cannot enlarge this chromatogram because if I would enlarge it, so we can go to 0.001 intensity, and then you will see no other peaks. It's about this small intensity. So there is a small threshold applied. If we don't apply the threshold, then the data will become very, very big. But even if we apply very small threshold, we see like 8,000 components in a plasma sample. So this is a fantastic result. So I think, it depends also from the type of the chromatography, from the type of the mass spectrometry, and so on. So there is no universal rule of what type of threshold you have to apply. So actually, it requires a couple of experiments manually to see what's relevant for me and what's not.
So what is the data reduction here compared to the normal raw files? If I store this kind of profiles compared to the actual raw, what is the reduction you get? What's that there?
Well, it is quite a significant reduction because we store the profiles. So you see all these chromatographic profiles, which is few kilobytes, and then we store data for all those triangles for the components. And because it's a data-dependent component, so you may have two identical spectra, so you may average them and so on. So you have the full variety how much information will be stored for this one triangle, for this one component. And this can be also defined. So I would like to have everything, or if this is if those are spectra coming from the same precursor, it doesn't make sense to store all of them. Well, just average them, so fuse them together. And you get a quite significant data reduction.
Okay. Thank you very much, Robert.
Thank you too.
Okay, and we can have more discussion. I'm going to just switch now to next. So it's Val or Adam, which one are you going to present?
Hi, Reza, I'm going to present. Do you want to make me presenter or you're going to drive the slide?
I can figure it out how.
the one at the bottom. Yeah, that might be easier.
Sign. Make the sentence.
You're presenting that?
Yes, got it.
But I don't know if you can.
Let me know if the people online can see my desktop.
Yes.
Yeah?
Yep, I can see it in front of you.
Okay. Yeah, thanks, Rosa. So thanks everybody for letting us present here today. I'm going to be presenting with my colleague. My name is Belty Yubi. I'm the lead scientist here at SciEx for Metabolomics and Lipidomics applications. I've met a few of you already, and with my colleague Victor and Adam, we're going to present to you what our data reduction approaches are at SciEx, and a little bit around about our workflows as well. And so the presentation is going to skip between myself and Adam today, who's also on the WebEx. So just very briefly, we're probably not really well known for our high resolution platform, and probably known more for our targeted platform. And so I just wanted to put up a little representation of the types of instruments outside of the Q-trap technology that we build. So we do play in high resolution mass spectrometry. We do untargeted metabolomic and lipidomic workflows, both from a data dependent approach as well as using data independent approaches. And we too suffer from all of the challenges that I've been listening to over the last couple of days in the when it comes to metabolomic type applications. So very briefly, our high resolution platform is called the Triple Top, and we can do a variety of different workflows, and we use a variety of different types of software. We have our own site-built software that we sell, but we partner with academic institutes to enable other types of software to be used on our platform. And so a recent one of these pieces of software that we helped, that we now sell at SciEx is XCMS Plus. And I know that many of you mentioned the use of XCMS during your workflows for untargeted metabolomic applications. So what we did actually was to enable our data and even other data from other vendors to be able to be processed, but enabling a local install. So I don't really need to go over what XCMS is, but XCMS Plus was built together with SciEx and Gary Suzak's lab. It allows us essentially what XCMS delivers online today as a platform, but it's actually been really streamlined and allows a local setup outside of the web interface that you use accessing the servers at the Scripps Institute. So what that enables us to do is actually process data much faster and actually allows us to upload raw data files as opposed to then converting them to these heavy MD XML formats. So I just wanted to list some of the benefits that we see, at least with the desktop version and locally installed version, that we're able to, for a typical data set size, this is a data dependent data set that we collected, or I collected on the Triple Top. It's around 3.5 gigs. And so we're processing the data in about an hour versus what we can do through the online version in 24 hours. We have huge, I think the second biggest benefit is the technical support with the software. And so the workflow process is exactly the same as you would do today. But like I said, it actually enables you to upload more data files as well as data from our own platform. As I said, we kept the platform open, so we recognize that technology will exist from other vendors too. I'm going to pass over this slide to Adam, and then I'll present back.
Okay, thank you, Bob. So when we start to think about all the data challenges that you guys have been mentioning, we really need to look at the entire system. So the management of all of those data files becomes extremely important. So you think about things such as file duplication. So are your customer data files already available in other repositories online? Are they available on company FTP sites? So instead of sending entire copies of these data files to Metabolomics, for example, can we just send a URL link to the file which is already available and shared? Again, related to data sharing as well, how well is your data being shared? Do you have to make a copy of it on a portable hard drive and then mail that hard drive to a customer who makes another copy of that copy, and then they share it amongst the company, and then there's several additional copies? So all these copies actually cost quite a bit of money and takes up a lot of resources. Other things to think about are the scalability. So what happens when your hard disk space is full? Are you using some distributed file system to really be able to handle that type of data and start to plug in hard drives as you need? So our solution aside is right now we have in proteomics and later on metabolomics and lipidomics to follow on. Our solution is the OneOmics project, which addresses these challenges as well as others, paths back to evolve.
Yeah, thanks, Adam. So I'm going to talk a little bit about OneOmics and some of the challenges that we see in data structure and even at a bigger level, trying to integrate all of these omics type data sets and the challenge that we see in systems biology. So even though we believe that today's biomarker discovery is going to lead to, say, tomorrow's personalized medicine, there are still many challenges that we need to overcome. And so omics data is going to be coming from multiple different technologies and multiple formats. And so the data sets that we've seen already, at least from the metabolomics and proteomics, are already very large, and they represent a broad range of biological conditions. And so the likely source of the various data sets will be across the different labs. So what we've been trying to do is develop solutions that allow us to compare and visualize all of that complex data from various different omics techniques. And so to do this, we want to build an integrated workspace that allows us to use larger projects where they can be completed, and an environment that allows us to process, compare, visualize, store, and share in a secure, friendly environment. And so the big data problem in systems biology is three challenges. The way that we see it at science, at least, is in fact in the volume, the variety, and the velocity at which the data is created. So I've been sort of preliminarily involved in the OneOmics project, but my colleagues, at least from a proteomics standpoint, have been doing a lot of the hard work input with Adam and with Victor and team here at SciEx, and I'm going to be involved from a metabolomics lipidomics standpoint. From a volume standpoint, processing, let's see, trying to bring together sort of genomic and proteomic data generates huge volumes, okay, in data size. At least one, if you take, for example, one proteomic sample, and you collect that in swap mode, which is our data independent acquisition mode on our high resolution platform, that one data file, if you collect that over a linear gradient, is around 13 gigabytes. And that's one sample. And if we then compare that to, let's say, one genome, it's around 100 gigabytes. So data processing can take days, even on some of the most powerful desktop computers. Movement, so the challenge to move that data and the results between collaborators, even from a local or global scientific team, is a challenge. And then managing that data, so large and longitudinal studies require these extensive data storage and on-demand access as we need, at least over the years of the collection of that study and further data processing. In terms of variety, there's a complexity in size, so the biological interpretation requires powerful visualization tools and statistical and conceptual tools. And there's obviously a wide variety of different types of this omics type data as well as the genomics. And finally, the velocity. So trying to easily and at a faster rate generate the data and shifting the bottleneck from data acquisition to actually analysis. So what we did here at SciEx, we introduced the Omics project. It's a result of an exclusive partnership with us and Illumina. And Illumina, for some of you who are already familiar, and if not, are the leaders in sequencing and array technology. And so the Omics project is actually an ongoing effort to bring together at least SWOT acquisition on our triple top, starting out with proteomics, as I mentioned, and then to build in the metabolomics, lipidomics aspects. And the idea is to bring together in a single workspace us to be able to process that data in a cloud environment. And so using an array of different applications, we host in BaseSpace, which is Illumina's application store and informatics community, to be able to advance the genomic analysis. And so the partnership enables BaseSpace to be a single location for, like I said, the genomics and proteomics big data, and allows us a secure environment to be able to streamline the analysis from all these multi-omic data sets. And so a little bit, just one last slide around BaseSpace and what it does before Adam talks about how we start to deal with data compressibility reduction. BaseSpace, so labs pursuing next generation omics, let's say, traditionally require the services of a highly trained bioinformatics team, let's say, and dedicated infrastructure to perform that data management, analysis, and storage. So what BaseSpace environment allows us to do is actually automate the bioinformatics analysis and the cloud-based software applications, scalability, some of the issues that Adam already talked about, such as data storage and management, and that sort of grows with your research needs. So the speed of analysis, at least from a proteomics standpoint, proteomic samples allow proteomic analysis of complex samples quickly generates gigabytes of data, at least what we're seeing here at SciEx, once you incorporate the technical and biological references. So processing that data right now can take days, and it ties up valuable computer resource, even on our highest performing desktop computers. And so what we're trying to do right now is actually free up a lot of that space and try not to invest in more and more sort of expensive types of computers. And so what we're doing is processing all of that data in the cloud, and we have been for the last sort of 6 months while we've been building, at least in the last year even, all of this infrastructure, means that we're able to process the proteomics data 50 times faster. And so we can actually crunch through a data set in a lunch break. And so what that means is, processing the data faster, being able to share that data, moving the data, as Adam was talking about, not moving it using hard drives. I mean, we even do that right now. I do that from a metabolomics standpoint. Not using FTP sites to move that data around, and all of the data is secured in one environment. And the environment, the cloud environment, is using Amazon Web Services, and it can be archived into something called Glacier for long-term and inexpensive storage. So I'm going to hand back over to Adam to talk about how our data files are constructed and then compressed and reduced.
Okay, thanks, Matt. So we'll just take a brief look at our data files. So currently, our data files are stored as binary files consisting of both metadata and the raw data itself. Our files can also be converted to different open source file formats, such as a common one is EMBL, which a lot of you guys use, which is available through tools such as ProteoWizard. When talking about these file formats, there are certain performance considerations. So the speed of access of your data, parallel access to enable parallelization of computation, the ability to read small chunks of data to avoid memory limitations. Creating the EMBL appears to have size and access speed overhead, related to the two talks today, the MD5 format built off of HDF5 actually looks quite interesting. Haven't played around with it myself, but after the two talks today, I think it'll be on my list. It looks like something to look into. The next slide, please. So going back to one of the original questions, so how can data file sizes be reduced? So yes, over-the-counter, let's say, lossless file compression algorithms do help. The compression ratios depend on the data itself, but for example, my computer's I've seen file reduction sizes of about 30 to 50% just using zipping the files. Since most vendor data files are proprietary, I won't go into too much detail, but in general, I think we continually strive to improve on them, and by making us aware of your challenges through these types of workshops, it really helps us really look into the future and figure out what types of data rates do we have, or data storage capabilities do we need, and really consider that in the future. So instead of focusing specifically on our and other vendor data files, I think we should really have a look at this at a higher level. Next slide, please. So once we have a good system for managing all of the raw data files, we need to really start to think about how to extract that information out. So for most vendors, file readers are already available. So for example, in ProUWizard, the readers are used to really read the information from the data files and convert those into open file formats. Go to the next slide, please. When we think about data reduction and compression, I think we also need to ask ourselves, where do we really apply these algorithms? We want to avoid the scenario where we have, for example, vendor 1 with algorithms A, B, and C, vendors 2 with algorithms D, E, and F, and so on. So it would be quite a nightmare to really manage all these different versions and algorithms depending on the vendor. So personally, I think a cleaner and more consistent approach would be to really look at this problem and apply the algorithms at the level of the generic XY data that's provided by these readers. So at that point, we can start to think about how to filter and compress this generic data, so at that level, and store it as an open file format on systems such as Metabolomics. And then, so assuming storage of these raw data files are mandated and have a good system for, and you guys currently have a good system for managing and sharing this raw data, for example, OneOmics is a solution. The next question is really, can we avoid making all of those copies of the same raw data? So the Metabolomics have to store yet another copy of these huge raw data files. So you start to ask yourself, what is actually needed? Can you extract out only the data for your confidently identified compounds? Are peak lists good enough? Maybe even within the peak lists, are the matching compound peaks good enough? I have an illustration of this on the next slide. Here we have on the top, so we have the raw data file, as you see on the top. So when you start to extract out data for, you can start to extract out data for confidently identified compounds. So you can see that we can it can choose, instead of storing all out in the spectrum or however large it is, you can start to pick up a subset of those spectra that you're actually interested in and you actually have confident IDs for. You can further reduce down each of those spectra or data by the various techniques that you guys have mentioned in this workshop, such as centroiding, background subtraction, noise reduction, and so on. And once you've really filtered that data down, we can start to look into compressing each spectrum on its own. For example, applying the Z-lib compression as it's typically done in EMBL. And then once you've generated that open source data file, you can actually run another level of compression to compress that data file on its own to smaller size as well. Thank you.
So yeah, I just got a couple more slides just to show you what we do with the data, at least on the Metabolomics side. Once we've collected it, I sort of briefly talked about it on the first slide, is that we'll take a data set and we'll push it through either XEMS Plus. So we can do all of our identification, peak picking identification in that software, or we'll do a different approach and go in and just target compounds. So that's using software that we currently have in-house, which is obviously more closed because we only read our own data files as opposed to Plus, which allows any format to be read. So I mentioned this before, when we're looking at proteomics, a single file, it can be around 12, 13 gigabytes, especially if you're collecting that using a data-independent acquisition over 3 hours. A small study of around 40 samples for metabolomics, not collecting data independent, but doing a data-dependent acquisition is around 10 gigs, so much smaller than that single swab file. But when we start to wrap that up and collect the data using the swabs, and currently the way our field is that we're collecting data not just in one column, but we collect positive and negative. So if I collect a data set, for example, around 18 samples, using a data-independent approach, applying K-link in positive and negative mode, and then doing reverse phase in positive and negative mode, already that data set's around 45 gigabytes. And just to explain that we have our demo lab facilities where we are also generating data for our customers. We do lots of collaboration projects where we're actually generating data as any other lab would be generating data. So we have to be able to store and collect and then share that data just like any of the other academic institutes and industry partners have talked about on the phone. The raw WIP files are taken and loaded for any data analysis, and as Adam mentioned, we can convert to various different formats to be able to put into other types of software packages further downstream. And as I just put a last bullet here, just showing that at least for XCMS, any data file can be loaded from any of the vendors, as well as many different other data format types. And I'm just going to pass over to Adam now to finish. This is our last slide.
Oh, thank you. So in summary, as technology advances and we come up with better and better instruments, we get more and more data. So in a lot of cases, the raw data files are actually mandated, so we can't really just throw away data, so that would be quite dangerous, as somebody mentioned, I think yesterday. Since raw files are still required, I think that data file management becomes extremely important. How do we avoid file duplication, as we mentioned before? How do we improve accessibility and kind of the shareability of the data, all in a secure environment? So what we've done here again is we worked on the Metabolomics project, and it's quite an existing, exciting project to work on, and hopefully we can keep working with you guys to really push it forward. So once you do have this better management of data files, we can start to look at what you really need to extract out of the data. So start asking those questions: what data is good enough to store in the tabloids, and then we can start to really look at the reduction in file sizes, I think. I think that's the last slide. Yeah.
Yeah, we'll be happy to take any questions that anybody might have.
Thank you very much, man. Any questions? I'm going to ask one from maybe either one of you about what is the timeline for this Metabolomics? When it's going to be, is it in operation, is it in use, or is it something that is going to be planned to happen sometime?
Yeah, Metabolomics has been launched this year. In fact, it was launched just at the end of last year, and we enrolled a 6-month beta test program where we went out into the field and spoke with our existing sort of key opinion leaders in the field, at least proteomics, and those who had access to these Illumina sequences, such as the MySeq. So it has been launched, and we were doing a lot of beta testing in 6 months, but it's live, it's free. Go up and sign up for an account. And I believe the link's in the slides, so if you want to download the slides, the link's in there. And you can start pushing up data using some of the apps. We're getting a lot of our, we recognize we are not the experts when it comes to, let's say, some of the more downstream, let's say, data processing, analysis, visualization, a lot of the statistical tools that are needed. And so as a vendor, we rely on working and collaborating with academic partners and so forth. So what we're trying to do is push out into the field, the academic institutes, our customers, our collaborators to get into base space and start writing apps. I know Gary Suzak's team have written an app for us, and we're going to push XCMS up into the cloud. But a lot of our collaborators are starting to do that. And think about it, they can start to charge their, once they've written an app and put it up there, they can charge on a per file basis. Right now we're testing the waters and it is free. I think we're just it's a very new space for us, which we're trying to explore, which is why we've kept it open and not charging, because we want to see where it can go. Okay, thank you.
One more question. I know you mentioned about having instead of different algorithms, have one, but I just want to open up this to everyone also, and you, whether that's any possible. Is it possible to have one algorithm for different formats? Because I would assume that the specificity of files and formats are very, very different. So I don't know if this one format is possible or one algorithm or several algorithms.
That would be a combination of algorithms. I think just looking at that generic data level and starting that space, and if it's required that we need, for this case, we need specific algorithms, then I guess that would be required. But just really starting at that higher level and trying to push everything to be more consistent, I think that's a good place to start before we really put constraints saying if it's this, then do that. So whether it's possible, I guess it's a matter of trying and then seeing if it is, but I think it's a good place to start.
What I'm thinking is not just compressing data, that could be one algorithm, but something more on data reduction, sort of removing noise, for example, baseline, that could be different depending on technology and the data required. It could be different, not necessarily in the same way, subtracting some information and kind of allow seeing results.
Yeah, I think you start layering different types of filtering, and once you've really filtered it down to what's good enough, then you can look at compression. I'm just thinking about compression itself. So it's layering in different types of algorithms instead of just one.
I think it might be able to, have one, or it might be one algorithm, but you definitely need to optimize it for different vendors and different instruments of a vendor. And I suspect that what we track and off data are actually quite different at the raw level, so you probably need different algorithms for that.
Yeah, that's kind of.
I fully agree. I absolutely agree.
Okay, thank you, Ed. So I'll try to switch to the next.
So Reza, I have an audience speaking from Sonic, so hope you can hear me.
Yes. Yes.
So could you be so kind to make Michael Clausley on the list of the presenter? I'm calling in via the telephone, but I'm sharing my screen on Michael Clausley's account. So if you could please make him a presenter.
Don't need to download that. Just go back to WebEx and make him the presenter. They're using their computers, they're not using local files.
Let's see the bar.
Participant.
You have to
Participant, go up. No. Up, menu.
Here as well.
Michael, down, Michael, House.
I sent them. Is it to Michael? I sent it to you.
Okay. I'll have
Okay. So I hope you will be able to see the presentation.
Yeah.
Okay. So first I would like to thank everybody for making this conference possible and inviting us to present here. It's really important for us to hear what you're thinking about and what the main problems are. And as a company that also produces dynamic instruments, proteomics, metabolomics, and operating such data science because of the high-res instruments. Because we get responsible to see what the needs of the community are. So during my talk, I will really focus down on the actual data and let's go into much detail on the solutions we have and more concerned with the open data formats that we want to import our data to, so that you, the people that do science, can work with and store it and process it further. So, and first, I really think that the raw data that we require with our MS instruments, they typically contain the complete profile spectrum. But the first level that we could reach to a really big reduction in data size is to say, okay, we don't really need profile spectrum for all use cases. We can maybe say, okay, we can limit this already to 9 spectrum. So this is a big step and a big possibility to reduce the data size during acquisition already. Files that can be used. After that, our acquisition software already implies both compression on the raw data, so the running, coding, zero profile data, and then the compression. So already at this stage of the acquisition of the MS spectrum, we are thinking and caring about the file design. Nonetheless, of course, as other vendors do, we saw that we can acquire data in our binary trajectory format, but we provide possibilities to export the data to open and the ability to do further filtering and already further compression. Up to now, our focus is always to have data integrity and completeness of the metadata. But if the community feels that there is a possibility to get rid of data that is not needed anyhow for specific applications, we are of course open to talk about what was our lossy compression and reduction in the data. For the exporting to open formats, we have a tool ready that is available on our website. It's called Common Export, and it allows all our customers, people that work with data, to export. So we have several high-resolution instruments that all match compact in deadline, but also Microsoft GPU older instruments are supported by this Common Export tool. I have as well about LC all the instruments for the architects and architects. You can apply this tooling and transform to open MS data. It's a simple Windows command tool that can use single analysis and batch conversion, so you can plug it into your workflow, into your analysis workflow, and it's now includes self-fetching archive that can be found after registration on our website. Maybe all the Excel formats are for email and data, and also some similar forms of JSON and CSV files that will mainly focus on the EMBL, XML, general the XML files. I already talked about the filtering of serial entities into compression. You can decide during this export your data in the open format to get rid of your profile data if you like, or you can say you want to keep the profile data and transport it to the open platform. Or the data set that you generate and the data for all high-resolution copy instruments. We are aware of that, but if you feel that you don't need the raw data, you're free to export pieces that just central to the line. XML and the data is not supporting compression, this is no way to get used to find that here without optimizing the data, like for EMBL, 1.1 imports, that data features that are available for EMBL. The tool is free to download from the Google homepage and runs on 7, 32, and 64-bit, but free charge license. It's not a source tool, but nonetheless, we are really interested in your feedback, and already this workshop is really interesting for us to see where the direction is going and which further open formats could be of interest. So the MP5 is really interesting for us. And we are really open here for further development in the community, and there's the possibility that we also expand the development of the expert tool, depending on your needs. So I guess there's now a good chance to find out what the community needs and what type of data are really mandatory for storing in the open repository. So it's really necessary that profile data has been stored on AD line spectra could be sufficient for the different applications. So this is mainly it from our side. I'm very open to discussion and for questions. Thank you very much for your attention.
Thank you very much. So I guess I heard that at least many of you are considering or interested now in more MZ5 and even JQI policy to try to use your example to show you compare those files to the MZ5 version as well. Right? Yeah. So this the big question for users really, data generators users. Do you see any parallel of it? Because I guess industry they would invest, they adopt it, they would keep an eye on it, but it requires some user base. Do you think that's something that will catch up or will not? Will still be?
It's true, yeah. Or not. Yeah, well, I think it's clear from the early discussions today that MZ5 is better than, say, MZML. The format is really been designed with efficiency. That's something that maybe needs to be fed back into the review process. Efficiency of efficiency of storage.
What about the NetCDF4? How's the status of that? Because that's another.
So
format.
NetCDF4 is completely stable. It's been used for quite a while. I mean, it's pretty much just a subset of HDF5 with simpler web API, basically. So yeah, that's perfectly usable. But there's the need, of course, to map everything that we have already in MZML into NCDF4 in terms of the metadata and the data.
The big question is who's going to take this tedious job?
Well, we're already doing that, but as far as incorporating the XML directly into NetCDF4 and having binary data in native NetCDF4 format. So we're in the process of doing that.
Is any I can test with try different variety of formats? I would say maybe you probably try a couple of formats, but is there any lot of difference between say one binary format to another, or is pretty much all
I can't
it's
answer that. Well, in what way?
In terms of conversion, in terms of adding benefits in terms of compression, structure, restructure, doesn't make any difference.
I would have to this kind of actually the NumPress paper went into quite a bit of detail across a lot of different vendor formats. So I would direct you to have a look at that paper. I was involved with that, but I didn't do all of the hard work.
Because that was exactly my reference point in my head, because the interesting part in that NumPress paper was that the dependency in it, they tried to hard disk and different type of compression that happened with different disks, solid disk versus some tape disk or some of the disk, and there are quite a difference, even in choice of hard disk. So that's something that not necessarily
in terms of performance, read-write performance, yes, definitely. Proteo Wizard could have a bit of better read-write access pattern to it itself, because, for instance, if you try and use Proteo Wizard across on a shared drive, it's vastly slower than if it's local. So,
it's sort of locally
yeah.
And what we're having, and this is the big issue when we do have data processing, which is more time to work
it's quicker. It's a lot quicker to copy to the local file system, do the conversion, and then copy back, which suggests that Proteo Wizard isn't optimized for reading and writing to a shared file system. But Frederick Lavander is the person to speak about these, looking at all the various different vendor formats. Exactly.
Looking at the future, something like NetCDF or future proof, as it's not just moments or
So one thing I'll say though is that that there's a big difference between format for binary data or large homogeneous binary data like intensities and NZs, and format for the metadata. Because having tried it myself, the HDF5 and NetCDF4 are awful for the kind of free-form metadata. XML is a nicer format for that. SQL is a very nice format for that. So it does have to be, I think, some kind of hybrid approach. But definitely the binary data could well be in NetCDF4 format. I mean, the MS imaging community already have the binary in a separate file than the metadata. So that's a good way to go. But NetCDF4 will just allow you to have the two things separately but in the same file, which is convenient.
I mean, you were talking about isotype as well. Is that something like it's an alternative with the data, or is it one to use that for the data to make it better structured?
I think because what I was saying kind of would be a nice prototype to try is that because isotype actually has a tabular structure, you can convert it straightforward into an SQL schema. It shouldn't be too hard, especially when you look at the sample part or the investigation study, parts where you actually record the samples or which factories want. Some of these tables are actually quite mappable to SQL. So you can make situations in which you keep the isotype standard that you invested some time and effort into as kind of interoperable. But then you can, for actual applications and uses, you can make some converters of SQL structure to isotype. Regarding the NetCDF, I just have, because we're talking about HDF5, NetCDF4 is built on top of HDF5. So I'm a bit, I would say I would defend more using HDF5 directly for the reason that I don't see NetCDF4 having that acceptability on sites. I think HDF5 is being used much more. And NetCDF5 was kind of an old project in which they said, okay, we're going to build it on top of HDF5 now, because they were lagging behind to a certain extent. So there is some concerns on my case. I think HDF5 would be much more transverse.
So what I would counter to that is that I've actually it comes to the same thing, because you can create the files with HDF5 or NetCDF4 as long as you make sure that you remain within the subset supported by NetCDF4. It will be perfectly happy to read them. So, and in fact, that's what we're doing, because we don't desperately want to add NetCDF4 as a dependency to ProteoWizard, whereas HDF5 is already a dependency of ProteoWizard. So we'll happily write out the files using HDF5, but then we can read them in using NetCDF4, and we can read them in across the internet using NetCDF4's functionality. So yes, I'm definitely in favour of allowing people to use whatever toolkit they want, just making sure that whatever standard is set upon doesn't use anything that NetCDF4 can't handle, and the stuff that it can't handle, I don't think is needed. It's really esoteric stuff that it doesn't handle.
So when NetCDF4 sees an item in a HDF file it doesn't recognize, does it choke or does it just sort of gracefully ignore it?
It'll ignore it. I can't exactly remember what it doesn't support. It doesn't support stuff that you wouldn't have, like for instance, in HDF files you can have references, so you can have the file system doesn't need to. It can be a directed graph instead of a tree, for instance. And NetCDF4 doesn't support that. So it's stuff that you probably wouldn't think about. And NetCDF4 doesn't support these variable data types, which MZ5 uses, but which you probably wouldn't think about first anyway.
You should try to avoid those at maximum because they're destroy any speed.
Right, yeah.
So you should make an exercise. I will avoid these as much, even if you're too. The thing is, by references, you're meaning it's the fact that, for example, with HDF5, you can actually iterate through the file and jump out of the file.
No. Well, I don't know, but I was referring more to pointers, so you can actually have a folder that, well, essentially like a symlink. You can do symlinks in, like Unix symlinks. You can do that in HDF5. One folder, symlink to another one.
Yeah. Because in theory, I think you can actually, this has been said on one of the things, it's a functionality, but be very careful how you use it, because you can make a giant blob of HDF files and just graph transverse even from one file to the other. There might be some applications on that, especially parallel.
So this unique data is the maintainer or
of NetCDF.
But that's what it comes from.
Yes.
Google.
Yes, yeah. I guess people, I mean, NetCDF3 has been used quite a bit in Metabolomics.
NetCDF is a very popular option to do XCMS. To use data rich compared to NetCDF, which is much more tidy than MZMLs. And you will actually do that.
Well, it just shows more lack of support for so many data. It's more than SMS. You've got raw data from a spine, but anything about that.
Yeah.
And it's very poor on metadata as well.
Yeah, it was very.
So, in terms of exchanging, is the most, it's been around for a very long time. Decades. Yeah. So it's been very well known. But it's compared to, I guess that's why I think it's coming back from NCDF as well. Yeah. Data are quite new in the website. One quick question, how you go about your tool? Is that they're using, is this based on some sort of library that you have in Brooker, which you're using your own existing library to convert the variable format to some open source, right? Just
Exactly. The library we use is called Compass Extract, and this is just a command line tool that gives the features of the library to easy access from the command line. For users, it's also possible to get the Compass Extract library EMBL. They can have API access. That's your question.
Yeah, that's what's exactly. I was just suddenly thinking about different aspects and realized I forgot to ask because somehow this is my observation. I might be wrong, but book has the most number of different flavors or formats. It's always difficult to track because if you get all these things, you get so many different flavors. So it is good that there's a tool that can actually read all the different formats and convert it to something that people want to access. So it's quite nice.
So if you have further questions on that tool, please feel free to contact us. We are also very open for suggestions for further file formats.
Thank you.
Okay, thank you.
From metabolites and adoption of these things, any comment?
Thoughts? Maybe mention about the isotype we talked about earlier in terms of using that for test case. The way we are moving that forward is moving more into graph-based representation of it. So JSON LD.
No SQL.
Yeah. And we are moving away from a SQL-based format underpinning our isotype. Because we don't want amplification of this information. Just as a sideline that there's APIs and stuff coming. Get the JSON properly represented out of an isotype archive. That's something to think about.
Maybe it's good to keep you in the loop of the development by design that you want to do something and then realize it down the line in a year's time or two. ISA point 2.
I looked also at the interaction at the beginning of screening, for example, how interesting it would be to use MongoDB. Maybe not anymore, another NoSQL or JSON to start implementing data. So, for example, the NMR spectra are quite easy to do because it's still relatively small. For the mass spectrum, I think it actually uses definitely not as good as APF5. But the part of the querying engine, I think the reason why I started using SQL was just to have a query language. So anything, I would say that part is quite, it can be many other things. Like I said, there's a Nature paper in which they use the SDQs, which is pretty much XML to handle metadata, and then build applications with the HDF5 with image data and possibly other assets. So they use the same binary on one side, XML. That's, to me, the advantage of XML is a bit, it's better to use SQL or maybe a NoSQL language because you get a query language. That's just it.
Yeah. Conversion, we haven't really committed to do any vendor-specific conversion formats. But obviously, ProtoWizard was less Windows. Well, it can't be less Windows dependent because the libraries and different softwares are Windows. In terms of API, that's an issue because all our clusters are Linux. We don't want to move into the Windows world at all.
Run it on the Unix. You can run it on the Unix.
Combine and stuff like that.
For what? For the user?
Yeah.
But it doesn't have all the library. So when you there is a software to run, but this is how I understood that you can do it. And there's a Linux version of it, but it does not cover half of them because the libraries are Windows libraries. You won't read them. So the tool is there, but essentially or doesn't do as well. Kind of stuff.
You started providing, before you needed to have Max things installed, and then you started providing with their DLLs. Yeah. So you go on Linux and it's exactly the same. You cannot really convert.
to talk about that plan, writing a paper, stuff like that?
Well, I mean, there are a couple of people still staying for the last day as planned. We're very grateful for that. So the plan would be, I spoke about the opinion piece already. There is this stuff on the web where we can work on, and I think everybody has some very specific and unique contributions to make. So we could really work in parallel tomorrow morning here in the room to write as much as possible, and then distribute for further ends. If that's okay. So we'll definitely be here, and everyone who stays is invited to join us for this spring event. I don't think that we need to discuss much more, and if discussions come up, then we can do this on the fly while we write.
So everyone, people online, anyone in this meeting is willing to be invited.
Absolutely.
And so
if people want to join from remote, then that's also.
So there is a link in the agenda that takes you to a Google Doc, which there is copy, there's maybe title and some sort of list of names. Please add if you think your name is missing, just add your names, and we probably format it tomorrow, and you can work on it and with your colleagues that are sort of relevant there and contribute to the, so yes. I watched them stand up.
So the plan for tonight is to meet at 6:30 at the conference center and walk over to the red line and then do what we did yesterday, essentially. And for all of you who are leaving tonight, thanks a lot for coming. I think it was a good meeting. I definitely learned a lot of things, a better idea where we stand and probably where to go from here. The Metabolomics community is much bigger than this room, and we have to, I think, reach out and tell everyone what we did. If there are no more remarks, let's close this meeting. Thank you very much.
Thank you very much for participating online and your time from different time zones to find it, and thanks again for participating and presenting.
I think I should say one more sentence. Thanks a lot to the people who actually did the organization. Chandu, Ken, Reza. This was well done, and I appreciate it. Thanks a lot.
Thank you.
Thanks, guys. Thanks for inviting us.
Goodbye.
Bye.
Thank you.